Good morning, everyone. Welcome to the morning coffee for Americas. Right now, the European hub, Europe, Middle East, and what was it, Asia? No, Asia was the APAC. So, Africa is right now having their wrap up. So, if you want to go there, that's fine. And we're just going to be here having some coffee with my very special mug today. So feel free to come around here. Morning, Katie, Arshita. So you can also ask questions at this point if you have any about yesterday, about the hacking, about whatever. Hi, Angela. Good morning. Hoping everything was good yesterday. Very cool. Even the beers. I saw that you were going to have some beers. Morning. So again, if anyone wants to have a chat here, I can poll you. And also, if you want to talk about the projects or whatever you have in mind, we can talk about that too. Coffee's good. Great. That sounds great. Excellent. Just announced that we are online. It says running a little late, so we'll be here in a bit. Yeah, of course. I'm really hoping to get into that one too. It looks like fun. So for people who are on YouTube, there's a brain visualization session today, put on by the Brainhack SIG, which is the part of the OpenSig. So the idea is to invite you there, and I'll just give the schedule now. I mean, we always go about it in the introduction, but I can just say what time is. So for EST, it will be at. Let me just look for it because I'm not in the EST. So New York, it's a good example of that one. So for EST, it says at 2:45, 14:45 hours. Yes. So at 2:45, we'll have the brain visualization train track. You wanna talk about it a bit, Eman, or well, we still have very little people here, so It's mostly the same people. Sure. People prefer that for some reason. Sounds good. I like hats. Sounds good. Yes. Yeah, I think there's a real need for visualization tutorials. I know I've been struggling to, like, I even asked Twitter for help with trying to bring Caret, or actually the Connectome it's called Workbench, into the same functions that Caret had, because supposedly you can do the same. But if you don't have any experience with any of those, it's really hard to convert everything you have, your figures and everything, to that. So that will be interesting to see. I'm usually using Mango at the moment. Mango is good. So what software are you talking about? Several ones or just one? The need for what, Pretty? We're discussing the brain visualization train track that is going to happen. And oh yeah, what I was talking about was that I was asking for help maybe like a month ago on Twitter, because I wanted to, for example, have results converted into something like Caret, but of course Caret is not longer being supported, so we're going for the Connectome Workbench. But that's also a bit it's not familiar to me. And I know that some people find the same problem. But yeah, you want to talk a bit, Pradeep, about your thoughts about visualization? There's room. I'm all for it. If you have coffee with you. Yeah, only mic is fine. I'll pull you and just put your mic if you're not ready for us. Cool. Yeah, Katie says there's cool visualizations in NiLearn.
You can disable the video. I know what. I don't care.
You can
Just waking up. This is waking up.
I can close your video if you want.
No, it's all right.
Right. Morning.
So, morning. Yeah. A ton of thoughts, actually. If you say anything specific, I can probably share my experience on that. So,
Yeah. Well, for example, so I guess so people usually, I mean, and I talk about only my experience, of course, but most people I know use things like the MRCron, for example, and I've been using Mango for a while. But having Lisa's here. So having like visualizations like you see on the Connectome papers, for example, where you have the inflated brain with the mostly cortex activations. Hi.
hello.
That's also
Yeah.
very interesting, but it's hard to get into, I guess, or at least for people that I know of, because, for example, the Connectome Workbench seems to be really good for that, but there's a lot of, I don't know, bells and whistles for that one too.
Yeah, so I completely agree with you. In
Hmm.
fact, I myself had been struggling for some time. I come from the MATLAB world originally. As much as I would like you guys to believe that I don't want to deal with it, uh, especially like the FS average visualizations to show where group differences are and how we actually visualize significant connections, etc. And people talk about BrainNet Viewer and sometimes CMTK that you mentioned, and
Yeah.
and stuff. I myself had great struggle just getting them to work, and then even using them sometimes, like the CMTK and stuff. And I don't think my technical skills are that bad, So there is definitely a need to really make these things easier, and in a way that's more. One of the problems with that connectome workbench, as powerful as it is, it's not accessible for regular developers, regular researchers. Think about a master's
Hmm.
student or like
Yeah.
an early PhD student, or even if you have the skills, you don't want to spend like a week or 2 weeks just to get one figure. You need to get that paper out,
I know.
and
Been there.
yeah, exactly. The gains are like really low for tweaking your figure. Once you get the basic
Hmm.
things done, right?
Hmm.
One of yeah, I think we discussed this a bit. Like some of us, at least in the last few hackathons, talked about improving Python ecosystem for surface visualizations. In fact, there is a channel on Mattermost called Surfaces in Python that we kind of discussed a couple of years ago, and I don't think went anywhere. Back then, Maya we had a lot of bugs and issues, and people couldn't really like push it because it's the only source of uh, um, powerful 3D visualizations for the Python ecosystem. There is
Hmm.
some connections to ITK and stuff, but they need to be glued in and then made reliable and easy to use. And we need a lot of energy and time there to get that
Yep.
done for people who need it, so to say. I think PySurfer has been useful for us a little bit.
Which one? iSurfer?
PySurfer, PY. It's a
Okay.
Python free surfer kind of
Hmm.
things. PySurfer. Very useful for us because I usually do a lot of particle thickness, ROI based visualizations and stuff.
Hmm.
And the inflations you talked about are easy there in a way. It's a pure Python, mostly Python.
Right.
Um, yeah,
Yeah, I guess for the new students, for example, it's hard to get into that, especially if your lab is not doing that. I mean,
yeah,
right now, it feels like it's a thing that if your lab has it, great. If not, then it's difficult to find it somewhere else.
yeah, yeah, yeah. Exactly. I was, I, what I was. I usually tell the hackathon people, newcomers at hackathon, you want to attend it because these are like a few hundred people who can really understand your pain in a way that no one else can.
Yeah.
And most of these people are not in your lab because most of us do unique things in our own lab, and often PI doesn't know what we're doing in terms of technical expertise and skill. If you
Hmm.
run into problems, this is the group you want to be talking to and work it out with in that sense. So uh, yeah, we need to probably spend more time, maybe a focused hackathon, like just connect home visualization hackathon,
Yeah.
late summer.
Yeah, that would be great. I
But yeah,
mean,
but
it
we need
should be
somebody to
easy.
really like lead this.
Yeah.
Uh,
I
we
think I
don't.
think I mean, in my opinion, I think this should be the easy part, right? I mean, the presenting good visualization should be like something you want to have uh, good tutorials so people can actually present work really well. And I find that that's the least I find with the tutorials. For example, I haven't found any like good Connectome Workbench tutorials, for example. for your own visualizations, I would say.
Yeah, yeah. Are you talking about the CMTK or which one are you talking about? Connect.
Yeah, yeah, because they have their manual and everything.
Mm-hmm.
But I don't know. For me, with my data, for example, it has been a hustle
Oh, right.
to.
Yeah, yeah, yeah. Gotcha. This is not easy. Yeah, yeah. I played with it.
Yes.
Yeah. And I mean, yeah, yeah. This is like that circos plot, the circular network connections that we see in computation biology and stuff. They look fantastic in these
Yeah.
fancy journal, and you're like, oh, I want to make that.
Uh
You spend a week, and I was like, you know what? No,
huh.
I don't need this. You know.
Yes.
uh, but I think a good we could certainly do a hackathon like 2 3 days in like few months from now, part of a global hackathon to um, get people together and solve what problems they have. For example, like you say, good tutorial, right? Just pick one popular one and then get it done with everybody, right?
Yeah, sure. So Aman wants to come in. Just going to
Sure.
say that when you come in, the video will pop up too. So I
Okay.
will disable that after. No,
Sure.
I mean not yours, Freddie, but Aman
Yeah.
since she doesn't want to use the
Yeah.
video as well. So just be aware that that will be on for a
It's all
second.
right.
Very quickly turn it off or
Yeah,
leave real quick
I will.
immediately.
I will. It's just that Pradeep asked me the same thing, and then he just bailed on
Yeah, I don't care.
that.
You got a pink shirt. You look great today.
Thank you.
Real men wear pink, you know?
Great. Yeah,
Yeah.
she's on now.
Thank you.
Aman?
I was actually gonna mention one software that I learned about. I think it came out a year ago. I think it's from MIT, but it's actually developed by a guy who was previously at UCL, and it's called Brain Painter. I
Okay.
haven't used it too much yet. The nice thing with it, unlike a lot of other tools, is that it allows you to also add color and data for subcortical regions as well, which is part of the problem with tools like PySurfer and a lot of other ones.
Uh-huh.
Yeah, so
Oh, that's good.
I can add that one. There we go. Thank you, CA.
Yeah,
Cool.
I can
I'm
share.
adding things to our document as we go along. So
Thanks, Aman.
if
So
I
you want to
can.
talk?
No, I agree with Pradeep in the sense that the chord figures with the multiple chords going from one part of the circle to the other, they look really cool. But I was reading someplace that I think maybe it was Russ Poldrack or maybe somebody else was saying that they look nice, but they're not very informative. But it is a really cool way for a network things to be visualized. So I'm just wondering if there are similar things, but that could be more informative than the way it is right now. Because right now I just feel like they look cool, but as a reader or as a reviewer, that's all there it is. It's cool.
You're talking about connections, right?
Yeah.
It's tricky, I guess. I don't know your opinion.
But I
Mine
think
is, yeah,
go
sorry.
ahead.
Go ahead. Sorry,
So
I have lag.
I do think that a document for beginners as well as more advanced folks in neuroimaging would be good. I think it's very needed. Different labs use different, they have their own favorites and they use different things, but because we're kind of stuck to a certain point as to what the lab is doing, we don't explore other options.
Yeah.
And to be able to do that and have, if we can even list like, oh, say Pradeep's an expert in this, and you're an expert in something else, a go-to person and who's willing to mentor and help would be very good. If people are willing to do that, there's no push for it
I guess
too, but.
So what can I think? What I would do if I was the king is a survey. Say again.
so tell us how you really feel, Pradeep.
Yeah.
You do it in Twitter, so you can just do it here as well.
Okay. So basically, I think it's important to learn where the community is at. Oftentimes, we don't know that. I like that you guys are trying to send the surveys every day, trying to hear what they say and stuff. And so for the few problems we discussed, reflect only whatever like four people we talked to today. And it may be somewhat representative of others, but I don't think I think I don't think it completely represents our community. What my approach there would be to email widely, hey, what is your visualization issues? Where did you get stuck? Pick one or two softwares that you need help with, right? And make them write exact one or top three problems they had. And then we collate them into a prioritized list of problems or issues to be solved. Set up a hackathon like whatever, this is June, right? September, and what,
Hmm.
you know, and get all the I would happily contribute. Like whatever the issue is, if it's in my skill set, I can sit a day or two, and if it's something important for the community, I get it done, right?
Yeah,
So
that's a good
I
idea.
would approach it like that rather than say, you know what, let's solve visualization issues and leave the whole people, leave the entire hackathon in a, what's the word, not incoherent, um, not focused.
Hmm.
Because what happens is people solve problems that they care about and they think are important, but often that does not move the needle for the community at large.
Yeah.
Sometimes it does, but not often. So if you learn, like, let's say, email all the OHBM mailing list and the NCF mailing lists and say, tell us your top three visualization, what do you call it?
Issues.
Issues. Like, what did you break
Or
with? Yeah.
wishes.
Yeah,
Wishes
exactly.
maybe.
Yeah. And then we collate that and focus on 4 or 5 software. I think we have enough expertise to and people willing to help. Like for example, I think many good people spend a lot of time on Eurostars, right? So why not like solve the issues, prevent the
Yeah.
problems in a way? And even we can probably even start with those Neurostars issues, and then see where problems are recurring. How can we fix them? And sometimes these software people who are developing the software, they probably don't have the bandwidth. How can we work with them to
Hmm.
really like make it more reliable and stuff like that? That's some thing I would support, like a focused hackathon. Maybe one time on visualization, one time on something else. There's ton of things we could focus on, right?
I mean, just a tutorial for brain visualization would be good to have as a project, right?
Yeah,
Say
I
again?
mean, Pradeep,
Like
if you want to organize,
a hackathon project for brain visualization, for example, tutorial or
Yeah.
something
Um,
like that. Sorry, what did you say, Lisa?
I was just gonna say that if you, Pradeep, or anybody else wants to just organize another virtual hackathon but specifically devoted to visualization, do it.
yeah.
I'll
I
be there.
could help lead. I could. How do I put it?
We can also, well, there's the brain web that Kachem was mentioning with the permanent hack projects.
Yeah.
Mhm.
So that's another good choice as well, I think.
Yeah, I would
Yeah.
also suggest to the open science room. There's like opportunity for emergent sessions during that, like throughout the actual OHBM event. So that could also be an opportunity to try to have a discussion about this.
Hmm.
I missed it, Lisa. Can you say it again? Sorry.
Oh yeah, sorry. I was saying that the open science room that's taking place during the
All right. Yeah.
actual,
Yes. For
so
sure.
there
Yeah.
are emergent sessions. So
So my point is that people bring it up, and we don't focus on them. That's what
yeah.
I mean to say. People solve one or two issues when they get stuck, whatnot. But I think surveying the community, and the problem is people don't respond, but that's another issue. But at least we make an effort to get a broader sampling and uh, put like a 10 to 12 issues really focused with software. And I think they kind of did it like in the last few hackathons. They used to survey saying, what tutorials do you need? before
Yeah.
they even like schedule it, right? And that's how they used to select the software to for inclusion in the train track and stuff. Similar ideas here, right? Just tell me your visualization problems, errors you keep having, or what would you wish you could have, what would you wish to make your life easier, so to say. And 2 3 days and we get it done and life is better.
Much
That's
better.
how I put it. Yeah. But I think the connectome bench problem you mentioned, that may not be solved because this is a more a fundamental thing. I think these people wrote it in C or C++, if I remember it correctly, and that presents a barrier, you know, unless you like often you want to tweak stuff. That's our moving target problem, right? You want to use it for basic things, and then when something new comes when you want to present it in a certain way, you want to tweak it, and then if you C++, it's a you hit a wall,
Yeah.
right? So that we may not be able to solve, but we could at least make sure nobody is in the limbo with bigger issues. Yeah. Oh,
Yeah.
thanks, Aman. All right. You don't
Uh,
want to hog up the space. Maybe if other people want to talk. I see Yarik and Chris. They're pretty sure they have
No
something.
one wants to talk at this time.
so what
Yarik must be up. Come on, Yarik.
I
Let's hear it.
so
Let's hear
I
from
do
you.
want to say something. I think
Sure.
the OHBM, if we are registered for the OHBM conference, we have access to the system for 3 to 4 months. So even if and even if we don't use the open science hours during the 2 weeks to start a document or to wrap up a document, we can take some time after the conference to do this. I realize people are really overwhelmed. They have too many sessions that they want to attend. So maybe it's not the best time to do another brain hack at the same time. But that's just my personal thought.
And I was saying like 3 months from now, or like 6 months or whatever, right?
Yeah, that would be
Yeah,
good. That would be good.
not now, not like next
Just
week.
like fully recuperate from all of this.
Yes.
Well, exactly. Three months or whenever, maybe during the second wave of coronavirus.
That's a grim view,
I
but that sounds
apologize.
fine.
Um,
I'm making the best of a bad situation.
It seems. Well, we're 17 people. It's not that bad.
so, I mean, I also think that other societies might be interested in that. I know Pradeep, for example, we have the Canadian Neurodegeneration on Aging, Canadian Consortium on Neurodegeneration and Aging, and they want to also try a hackathon this year, but they have absolutely no experience whatsoever. So Pradeep, you should probably get more involved in that. And they want to deliver a product. I'm part of it. I'm the chair, so I've tried to dissuade them from trying to deliver too many products in 3 days. But it's their first time, so let them go through the experience. And we can list topics. So one of the topics, what I could suggest is brain visualization, which can then at some point link in with the OHBM brain hack team as well. So, and that's just one organization I know of. I'm sure there are others. So just to, if we are doing COVID and we are going virtual, then there's no reason we can't integrate things as well.
Hmm. Yeah, sounds good too.
No, so let me. I basically like we have like what 26 people. What I was saying about Chris and Yarik was that they are experienced and they probably have run into similar issues. From maybe have some good ideas on how we can go about solving them as a community, to prevent recurring issues, or at least remove certain barriers that we could have removed in with a few days of work.
Hmm.
So yeah, yeah.
Anyone wants to come in?
Come on, Yarik. Let's force Yarik to talk. Come on.
I can just send the invitation, see if he wants
Yeah,
to.
yeah.
But we can be 5 here, right? Just without one of the, or not.
We can try. I'm not sure actually, because I know that it's 4 screens that we
Mhm.
have to, that we're limited to. But I'm not sure if one of the people is only using a mic.
No, yeah. So, Chris, the issues we're talking about are like, for example, the difficulty in using the Connectome workbench. It's complicated, and for example, difficulty in generating 3D mesh visualizations. And we discussed that, I think, before. Surfaces in Python, and there are other pesky visualization issues that keep coming up, especially for novices not knowing what is out there or how to get along. I think Aman was suggesting a collection of software that,
Mhm.
like, I think they may have collected it already in the Markdown. I know learning resources was comprehensive. I wasn't sure if how comprehensive it is in visualization. Maybe Rennie can talk about that. We could add the stuff there, but I know there's definitely a few visualization issues, like 3D mesh visualizations and easy connectome visualizations.
Yeah.
There were issues for me, and I imagine there are issues for a few other people out there too.
For me as well. I mean,
Yeah.
I mean, and then also another thing is that you might feel embarrassed that you don't know this. I mean, or I do sometimes, like, oh, how would I? Why do I don't know how to do this image, for example? But and I know that a lot of students feel the same way. But it's just it's not easy to approach. Sometimes it's just or is it organic for a lab or is it not? I mean, either you have it or you don't. I feel like that's the way it works. So even if you look for a lot of things, like for example, Mango for me was very easy to implement, very very easy. But other things, it varies.
Yeah. Oftentimes labs don't have the expertise. Most of the PIs are from like the medieval age. They only know MRI chrome and nothing else. And nobody to train and yeah, so to say. This is true. Like, if you work with clinical collaborators, this is the issue sometimes.
Hmm. Yeah, but also when you work outside of like hubs like the US or Canada, UK,
Oh yeah,
that
right.
gets really difficult. I work with a lot of
Exactly.
students from
Yeah.
India, for example. I have a good collaboration with India, and when they come here, I have to teach them some of those things sometimes, and sometimes they already know some other things we
Yeah.
don't know, so it varies a lot.
Yeah. Yeah. Um, yeah.
Yeah, we could suggest. I mean, Yarek's suggestion. I think that could fit in with CONP potentially.
Yeah. So yeah, um, that helps for, I think, some of the basic issues. I think there's 3 sections at least. People who just wants to put some CSV in the browser and get a visualization and put it in their Word document. I think this solution would definitely help them. There's people who need to um, automate a little more of that, for example, multiple panels and stuff like that. And there is people who wants to really like customize it too, right? I think we were referring to maybe, yeah, sure. I don't know how many people depend on data hosting portals now, especially when they're analyzing new stuff, analysis platforms. You mean like something on Open Neuro, Yarek? Like, process, run your bids app, get something out, and then connect it to another visualization app?
So I will be interested in also like what Chris is saying about NiLearn, because I know very little about NiLearn, and
Mhm.
it seems to be there's a lot of development on that.
Yeah,
Chris,
yeah.
would you like to come on stage?
We were trying to get a speaker online, NiLearn, but it was too last minute, so we couldn't include the speaker, or she couldn't commit to being recorded by the time it needed to be recorded in. But definitely it was on our agenda, and we
Oh,
should.
yeah. I saw the
We
bio
should.
image lead. Yeah.
Yeah,
Well,
yeah.
I think I need to lose a person to invite Chris.
Okay,
Who wants to go? Thanks, Pradeep. Thank
No
you.
problem. Yeah.
Thanks, Pradeep. We'll be in touch with that about that. Okay, so let me just invite Chris.
Perfect.
There is something. Okay. Good.
I'm happy to go too if others want to come on screen. That's fine. I can type away.
Chris,
Sure, no worries. Hi.
Sorry, I'm backlit.
it's
I
fine.
can
Thanks
try
for
moving somewhere else. Yeah, so Pradeep's thing about Open Neuro made me remember. So I don't know if you guys have looked into Brainlife.
No.
So that's a project fairly similar to Open Neuro, but they're less about the data hosting, more about the processing. And they've implemented a bunch of viewers so that you run it and well, I'm not sure if they've implemented the viewers or just managed to integrate them pretty well. But so if a data type has been defined as like we know how to visualize this, like you just pull that right up on your browser, which is pretty awesome. And Pradeep says it's more batch processing. It can be for batch processing, but you're usually, I mean, I've only played with it so much, but a little bit playing with it, you try out a pipeline, you start to construct a pipeline, you try it out on one subject, you can sort of explore that, and then you scale it up to batch processing, just saying, now I want to run it on 300 subjects. And so it's very flexible. Sorry, just a second.
Yeah. I'll just mute you and for now. So now we're populating the document. If people want to contribute, the link is just down there, here.
And actually, one thing I would ask, perhaps like when you're adding a resource, if you could actually just add some caveats, because I think that's one of the problems that I think, especially for newcomers, they hear about all of these tools, but they don't necessarily know what the limitations of the tools are. And I think a more experienced user, that would be probably one of the best things that we could contribute. Not really necessarily, but somebody even more experienced.
Yeah. Yeah, I'm guessing people have different experiences with different software.
Yeah, and perhaps you could even like, oh, sorry, Eduardo.
No, go. I
was gonna say perhaps one thing would be to list limitations of the tool, and another would be perhaps if you already have examples of a figure in which you've used the tool, to perhaps link to that. That could be helpful.
Yeah. Yeah, also it would be nice to like have a paper and say, I want to do that figure. How do I do it? And then have a small tutorial about that one, for example.
Oh, thank you for whoever just made that table.
Yeah, I thought it was you.
Oh.
Doesn't say who is, but that's good. That's why we have this.
Yeah.
So yeah, like for example, Caret is no longer supported. That's a problem. There are some small tutorials out there which have worked for me, but still. Oh, thanks, Betty.
Yeah. Thank you, Pradeep. Yeah, I guess if there are any project leads right now who want to like give an update, we can do that in the last like 15 minutes before the intro session starts. Otherwise, we can continue chatting about brain visualization or I don't know, any other topics.
Yeah. So what do you use for brain visualization yourself?
Me? I've been using NiLearn a lot. So I had used Caret. I mean, I'm also like relatively new to neuroimaging. I mean, I started it 2 years ago, really more like actually doing it, I think, like often a year and a half ago. So I would say that one of the first tools that I was taught was Caret, and then honestly, I've just been using NiLearn for most of it.
Okay. And what's your experience with NiLearn?
I really like it. It's very easy to use.
Hi again.
Yeah, specifically, hi Chris. So for brain visualization specifically, I've been using NiLearn, I would say, predominantly.
Great.
Yeah.
Chris, do you have an opinion on that? No, I'm just back. But yeah, I guess NiLearn is my primary thing that I use for visualization. In my PhD, I ended up just writing all, I did everything in Python, but then visualized in MATLAB because we had some existing plot things in MATLAB. But NiLearn has pretty much everything I would have wanted back then. So that's all I would really try for now, unless I was trying for a really specific thing.
Mm-hmm.
Yeah, and regarding what Amonpreet said, yeah, Plotly does have some really great features. I've seen examples of like Plotly dash examples for really cool grain visualization. Yeah.
I haven't used that one. So Pradeep is going at it.
Plotly is neat because it's kind of easy for people who might not have any coding experience, and it could help them learn coding as well, like in a way, because you can either do like a completely like basic interface where you don't know any coding, like how you would do it in Excel or something, right? But then it converts everything into 3 different languages. And if you're a Python coder, you can use your Python code. If you're using some other language, MATLAB, then maybe you can even do that, or R. So it's a multi-platform, and they have several free features. Now, if you want to do something too intensive, you do have to get a subscription. But they do give reduced rates for academia, and they're very approachable. So if you need a feature developed, they're quite into talking with you on that. So I'm not suggesting it's the be-all, end-all of things, but something to check out if people are either new or advanced.
And Eric is mentioning Data to Viz, which I've seen before too. It's a great website, I would say.
So does this do plotting or just show you different ways of plotting data?
I think well, I've used it before once, but now it's huge. Wasn't like this. It gives you ideas of how to present your data, depending on what you are actually doing.
Oh, but then if you click on, say, pie chart, it says here's our Python D3 gallery. That's pretty cool.
So I'm happy to go off and have somebody else come on screen. I feel like I'm hogging up space here.
Don't worry, but thank you.
I see Eric just joined the chat. I don't know, Eric, do you want the screen again?
Are you presentable? Thanks, Aman.
Thank you.
It's not even 8 o'clock. I don't think anybody's presentable.
Where? Oh, right, you're in California.
Oh no, I'm in New Hampshire, but he's in Oregon.
Okay.
Maybe he doesn't sleep. You never know who doesn't sleep.
Or he just sleeps in a 3-piece suit.
Always presentable. I love it. Sleep sitting upright in a suit, or
I'm enjoying listening to this, but now I'll be a part of it.
Yeah, now we can judge your appearance, not just how we imagine it.
Yeah, I'm a handsome guy. I mean, come on, right? So, yeah, I have a 4-year-old, so it's right. I don't really sleep as much as I could.
I understand that.
Yeah, my hiatus a minute ago was also from a 4-year-old.
not relate. Sorry, guys.
Don't worry.
I can't relate with old me.
I was just gonna, I guess, tout Data to Viz's horn for a bit. So I just sort of stumbled across this website on like a Google News feed a year or two ago, and it might have been longer than that. But what I really like about that site is, you can flip through the Explore tab, whatever kind of data you have, numeric, categoric, or both, or maps, and they sort of have a flowchart for no matter what kind of data you have, they have suggestions for common uses. And like, let's say you're looking at a numeric chart, like, let's find a good example, a box plot. As soon as you click on box plot, it tells you about, actually, can I share my screen? Or would we have to kick somebody off for that?
No, try it.
Okay, let's give it a try. Too many video sources. Stream is limited to 4.
Okay, and kick Chris.
Sorry, Chris. Okay,
let's see. Automatically did that.
My bad. Okay, so can you guys see this?
Yeah, I'll focus it.
Yeah.
Okay, so there we go. The top page, when you get there, guides you immediately to Explore. And then within the Explore, they've got these different data types that you might have that you're trying to plot. So if you look just in the numeric, for instance, let's say you have several numeric variables and they're ordered, then you would go down this little tree. And you could say, okay, well, I might do a stream graph or a line plot or a stacked area plot. Let's look at stacked area plot, for instance. If I click on it, then it tells you things about stacked area plots, common mistakes for usage with stacked area plots, and then there's code for how to do stacked area plots in different languages, which is, I think, just awesome. There's even a dedicated page that I think has all the same information. But so if we look at D3, for instance, see what they have. They've got a few different versions. Here's a really colorful one, so let's click on that for fun. And the code is right there. So like you can immediately take what's there and start playing with it or trying it out. And I just think that's super. It's like a great way to get your hands dirty immediately, no matter what languages it is you want to try out. And I don't know. I think it's really cool.
Yeah, it is. Something like that for brain imaging would be amazing.
Yeah.
Hard, but amazing.
How do I get back to? Oh, you guys are in the same tab. That's why I'm lost. There we go. Ah. How do I? Thank you.
No, thank you.
There it is.
Yeah. I think that a lot of people will find that very, very informative. The data to this.
Yeah. But I feel like I've now taken over the conversation. I like sharing stuff about data visualization whenever I can. So like in our project, we're working with data visualization stuff right now. We just got our data last night into a nice shape that all the swipes for science votes are one per row, and it's in the GitHub repository, and it's all happy. But now we gotta produce some visualizations. So today you're gonna talk about the schedule soon for today, right? And
that's in 6 minutes.
Okay.
I was just through the chat and I saw that Per Herholtz is on here, so I don't know if he wants to join. I just asked him. Okay. One more person.
Yeah.
I know Per has quite a bit of experience as well with NiLearn and BrainSpace, which is developed by BMNI. And Reindeer, one of the developers of BrainSpace, is also presenting during the Brain Arts Day presentation. So if anyone else wants to join. We could also take like a brief break before the next session. We could end this early and people can, I don't know, get some food if they want to. Or coffee.
You want to get coffee? Is that?
I have coffee. I
good.
want to get food once again because I still haven't had breakfast as always. Oh, okay. That's all right, Per.
Okay. So yeah, we can wrap it up for now and then just have people come back in 5 minutes. Would that be good?
Perfect,
Eric?
yeah.
Thanks for having me again.
Yeah.
Thank you. Take care.
See ya.
Bye. Cool. Hi, Rami. Rami, do you want to join? Cool. Okay, then I guess we're not taking a break.
Okay.
We are being invaded by the Europeans, Chris. That is correct.
Yeah, because they're up already. So I just invited Emmy.
Hello.
Hi.
Hello, everyone. We've literally just finished.
Oh, really?
Yeah. I just waved goodbye to the European hub, and I'm saying, "Hi, Americas," and I'm not hyper at all.
How many coffees have you had today?
One, but the cup was about the size of my face.
Sure. Was it espresso?
if you guys actually want a great example of just how tired Remy and I were yesterday, we recorded an outro video that's 15 minutes long. I don't know how comprehensible it really is, but yeah, it'll be presented today during the closing ceremony.
I've not rewatched it. I joined the Asian Pacific Hub this morning for their wrap up to actually do the thank you, and I was like, you don't have to show the video, you can just use the slides, and they were like, oh, if you're here, just do it. I was like, okay, fine, I'm good. Yesterday was super tired. I'm a bit better now, but definitely.
Yeah,
I don't know how everyone else in the crowd is feeling. Oh, hi from Europe. We're getting a lot of people just dropping by.
Wow, so many invaders. Hi, Salim.
Yeah,
Hi,
I know.
from Europe, but
so yeah, I guess everyone is just like, oh, we're done with that one. Let's go to this one, right? I was just explaining people in the European hub that I think a few of us amongst the organizers want to be in complete denial that this could be over. So on the European hub, we're like, no, we're going to make it continue. So we're going to crash the party of the Americas. Just kind of keep we want to make this continue just a few more hours, please.
Yeah. It's true though. We spent basically a whole year planning this, and then it's really just, it's a 3-day event that's gone.
Yeah, it's just like this. Yes.
Yeah.
Yes, Salim, if you want to come on stage. It's been so long since I've seen you. 5 minutes ago.
Not
So,
no, we were broadcasting the video, so it's been kind of more than 10 minutes.
Wow.
Yeah, I missed you.
Adorable. I love it.
alrighty.
Oh, man.
Actually,
It's really amazing to see you again in America.
yeah, exactly. Wow, we've invaded teleportation, right?
Yeah, and I'm not
Pretty much.
dead like that. It's nice.
And actually, Selim knows the jokes, but this morning, right before I left, I was on the morning coffee in European Hub, and before I joined, and on my way out of this to go to the wrap up of APAC Hub, I just left the video by just going energize, just because a Star Trek reference was just in order, I think. Yeah, sorry. That's the level of silliness that I was at today. I am sorry.
So
It's like I'm seeing the same names in the chat, so I'm like, wait, have we moved place? I'm so confused. What is going on?
So we have 1 minute to start the other session.
Oh yeah, so I think we're gonna have to end
Yeah.
We're gonna
Thank
vacate the place and get you let you start your actual show. Okay, cool. Have a good day, everyone. Enjoy. Ciao.
So, okay. Let's move on to the introduction.
Yeah.
Maybe people will have 30 seconds to prepare.
Yeah. And then I guess yeah, I guess I can. It doesn't really matter who screen shares. This document isn't very long. I can screen share and go through it.
So let's just let me log off and then you can log in.
Yeah. I'm still going. My bad.
All right. See you later.
Yeah. Hello again, everyone. So now we're just going to be doing a very brief intro of everything that's planned for today. So I'm going to share my screen so that I can just have the notes on screen as well. Give me 1 second. And I'm humming again. Sorry, everyone.
It's not annoying though, but so don't worry.
Okay. Cool. So 1 second. Do you guys still see it? Yeah?
Yeah.
Okay, just double checking because it's annoying because I have to be on the actual tab in order to present everything. But anyway, so today we once again have quite a few sessions for the train track. So we have one session for Docker and Singularity, which was recorded by a few people from the APAC Hub. We have a session, an intro to machine learning session that uses both scikit-learn and nylearn. And as a warning, this one goes a bit over time. So we allocated an hour and a half to it, and it goes a little bit over that. So just a quick warning, we were warned by both the Europe, Middle East, and Africa Hub and the APAC Hub that we may end up being a bit behind schedule. And then we also have 3 presentations from the Brain Arts SIG, which I'm very excited for. So I'll just read this message from the Brain Arts SIG. Their mandate is to encourage people to share their visualization experience and submit their work to the art competition at the Organization for Human Brain Mapping Conference. And neurodiversity is their theme this year, and they're trying to reach as many different audiences as possible. And so there are a few links over here, and I'll actually just link this document in the chat as well, or Eduardo can do that right now. And yeah, so we've included the slides for Reinder's presentation, as well as the manuscript, GitHub repo, and the README associated with that. So one of our sponsors, INCF, the International Neuroinformatics Coordinating Facility, they presented a session during the Europe, Middle East, and Africa Hub. So they have a YouTube link that you guys can all watch as well. Otherwise, yeah, so the hack track continues today. We're going to have a wrap up at the very end of the day. We are going to invite all of the different project leads to present the progress that they've made over the course of the event. And we also encourage everybody to sign up for BrainWeb. So the OHBM Brainhack only happens once a year, but the point of BrainWeb is for it to continuously happen over the course of the year, and you can just have these continuous projects. Then Remy Go created this hot takes feedback form, which is very similar to one that Roberto and Katya put out last year. And so here, literally just add any pros, any cons, just literally word vomit your entire experience over the course of this event. It'll be really useful for the organizers next year. Cool. And I will close that.
I think Remy's mentioning that we didn't mention, or did we mention on conferences? We have 3.
Thank you, Remy. Yeah, sorry. We also have on conferences that are happening at 2 p.m. EST. So I'm going to try to find that document. Or
we have about 3. Yeah, I was doing that.
Okay.
It's cool. Not handy, but let me just see if I can get. Yeah, I have it here. So just go to the Americas. So we have 3. One by Cooper Smout, Dorota, and the con is presenting also. I think it's Christine who's presenting, and maybe Remy if he's energized.
And I'm also adding a button down below for the document that I just went over, and that'll have the link to the YouTube video that INCF recorded, links to the Brain Arts SIG videos and notes, etc. I think I also need more coffee. They still said the second rule of Crowdcast is you don't talk about Crowdcast. True. And to Remy, I really like the expression word vomit. I feel like it's a thing that I do constantly, and I apologize to everyone who is subjected to it. Yeah, so we have 7 minutes before the Docker and Singularity session is supposed to start. So if anybody wants to come on stage, for those of you who weren't with us for the welcome session and that just happened in the previous hour, we had a really great conversation about brain visualization resources, and I started an HackMD document for everybody to list their resources. Alejandro said, in terms of timing, do we have enough time for more? If so, how many? Are you asking about on conferences?
So I'm just linking the visualization software that we have.
Perfect. And then Eric asked, are the on-conferences for the project wrap-ups, is there a difference? Those are separate. So the project wrap-up has its own dedicated section during the closing ceremonies.
Yeah.
Cool. Yeah. So we could also just start the next session early. That's the other option.
Yeah, sure. I mean, we want to go by the visualization software. Pradeep has done a great work, and other people are putting on a lot of things now. So there's a lot of visualization tools, and hopefully we'll have more when this finishes.
Yeah.
All right.
Last chance. If anybody wants to come on stage, say something for 5 minutes, you're welcome to do so. I could
Otherwise,
also randomly select a human again. My favorite thing to do.
it's like chat roulette. That wasn't good actually. Chat
Yeah.
roulette, remember that?
Oh, I do remember that. Oof.
I'm old.
Cooper, cool. I will invite you.
Oh, great.
Yeah, I just sent you an invitation. Hi. How are you doing?
Good. How are you?
Hi.
Good morning, I guess, for you.
Morning.
Yeah. Are you in the APAC hub or the Europe, Middle East, and Africa hub?
I am, yeah. It's technically morning here, but it's 1 a.m.
Yeah, okay.
It's been the end of a long day. I'm about to go to bed, but I did put my name down for a, hi Remy.
Yes.
I put myself down for a unconference on the naive belief that I'd still be awake at 4 a.m., but I don't think that's going to happen at this rate. But I thought if I could just make the pitch that I was going to make at the unconference.
Yeah, go for it.
5 minutes.
Sure.
So yeah, I just wanted to introduce a project that I've been working on for the last year and a bit. It's called Freer Knowledge. And basically, it's a collective action platform for academics. And it's kind of based on the premise that like science in general is kind of like a giant collective action problem. Like there's a place that we want to get to, let's call that open science land. And there's a place where we are now. And the way that everything's so interconnected, it can make it really difficult for us to move forward as a community and get to the place that we want to be at. And to me, like the most obvious example of that is the publishing industry, where we're still using these, archaic journals that are owned by commercial corporations and not really letting us make the kind of progress that I think we could be if we were in control of the system. But we're all kind of trapped into using these journals that we don't really support or want to support. And so this means that like really awesome new journals that can start up can struggle to get the foothold that they need. And in our field, a great example is called Neurons, Behavior, Data Analysis and Theory. Do you know this journal?
No, I don't.
I don't know if Conrad Cording's around, but I don't know. Can I also share screen?
Yeah, go for it. Perfect, and I'll just focus on it.
Is that actually coming up? Doesn't seem like it is.
It just looks like it's loading, but yeah, your screen is shared.
Okay, cool.
Yeah, it's shared. I can see it.
This is the journal that was founded 2018. And they've got a really broad remit. They'll take a whole bunch of different neuroscience and behavior and theory papers. And if you look through the editorial board, they've just got an amazing board. Like, feel free to check it out and see who's in your field. But there's basically this amazing community of people ready and waiting for articles. It's if you check out what the journal is, it's effectively all of the things that I'm sure everyone here supports. So it's open data, open science. It's free to publish. Well, I think $10 to publish, and open access. So we've got this like community-driven journal that is really doing the right things, and all it needs really is the valuable input that we're currently sending to Elsevier and Taylor and Francis and such. And the problem from my perspective is I'm an early career researcher. So if I was to send my papers to this journal right now, I guess I'm worried that I might not be able to get that next job that I need. But if I knew that, say, 1,000 of my colleagues were also willing to send their articles to this journal, then I'd feel a lot more comfortable dedicating my work to this journal. Yeah,
Can you post a link,
put it in the chat box now.
Yeah, because we have to wrap up in a bit, but just so people can have it.
So yeah, that brings me to the platform. which is basically this collective action platform that we've built, where you can join campaigns that you believe in. And the idea is that you sign onto a campaign, but you don't have to do anything until you've got the critical mass of support that you want to see for that campaign. And so I haven't created a campaign for this, but we could have a campaign where we all commit to supporting this journal when, say, 1,000 of us have agreed to do the same, or maybe 100, or whatever the number is. We could talk parameters. But what that would mean is that then in a very short period of time, like a couple of years, this journal would be able to build the reputation that they need to become self-sustaining and then compete with the likes of the Elsevier journals at the top of the chain. So yeah, that's my basic pitch. I created a channel, which I'm not going to be able to monitor because I'm going to bed. But if anyone wants to link up, please, I'll put the channel in there and you can catch me on there because I'll be hosting the HBM Open Science Room next week and would love to chat with anyone's interested in this.
Yeah. Cool. All right. Thank you so much, Cooper.
Thank you. Bye.
All right.
Cool. So then I'm going to end this session and I will move everybody over to the Docker and Singularity train track session. And so those of you who want to just keep working on a project, you're welcome to do that. Otherwise, I guess we will see you during the Q&A then. So.
but sharing your pipeline and making it reproducible is actually very important for us. So it can lead to significant differences in long pipelines, as we say. Okay, so I'll just give a couple of use cases. So for example, in my master's, I was asked to rerun a FreeSurfer analysis from 5 years ago using FreeSurfer 5.3. So what would you do? You go to FreeSurfer, you download and install FreeSurfer. You want the different versions, so you go to the version page. You find 5.3 wherever it is, down here somewhere. First of all, which one is it? There's 5. And then you click on the one that you decide. And then you look in here. What have we got? So we've got one on Mac OS, and we've also got one on CentOS 4 and 6. The problem with these now is that some of these actually won't run anymore on some of these older systems. Or if you have a Mac, I mean, Mac or Apple forces you to update your system at some point, and you will have to update from OS Lion. So it may be impossible or very, very difficult for you to run a FreeSurfer analysis from 5.3, which is why containerization can be very, very useful. FreeSurfer 5.3 also causes a library error, which was the same library, I believe, that we were talking about before. So it may be very useful for you to use containers in this example. The next use case I wanted to talk about was scalability. So for example, you want to run fMRI prep on your pilot data. So you've got a bunch of fMRI data. This is you, and this is your scanner. This is Eamon, our radiographer at CAI, and this is our participant that we just got. So we've got a pilot data, and we want to run it through fMRI prep. So what happens then is that suddenly Eamon goes and scans 100 different people. And we've got all of this new data that we have to include in our pipeline. Now, thankfully, scaling with containers can make things very, very easy because you're using exactly the same code as you did in the first instance with your pilot data as you were with 100 participants. So what you can do is you can use the same software on different platforms. For example, now you're using a HPC instead of your crappy laptop. And you're using exactly the same code, exactly the same software, and it's all containerized within, say, a Docker or Singularity container, and you're running exactly the same code and the same input, which is why some of these things are so useful. So you can run the same thing and scale it up infinitely, depending on your compute systems. So yes, you can run the same pipeline with no changes, hooray. The next thing, running things on different operating systems. So example, you've got your terrible laptop here and you're not looking very happy, and you go away and you spend $2,000 on a brand new Alienware computer. Now what do? You've got a new operating system, for example. Let's say that you've changed from Mac over to Windows. Now what do? Well, with containers, you can run Linux software on Mac and Windows, and you can run Linux software on Linux as well, obviously. But containers will make your work reproducible and robust to operating system changes. So it doesn't matter what your underlying host operating system is. With containers, you can run the exact same sort of light operating system on your computer that you are using and the operating system that you're using at the moment. So that really helps in the previous example where you go from using your local computer up to a HPC, which will usually be Linux, and you don't have to change any of the code. Great. Our next use case is sharing. So here you are, you want to share with all of your friends. Next thing, in this example here is a paper that we recently published looking at segmentation of the hippocampus subfields. And what we wanted to do was actually share our pipeline, our analysis, our software, and our code, and all of our data all at the same time. And so one way of doing this is via Singularity and Docker through containers. What we could do here is actually publish an instance of our code, of our software that we use, the operating system that we use, and also all of the data, push it all into a single container, and then anybody who wants to use it can now reproduce the entire pipeline, including the data and including the code and including the software at the moment that it was run, and reproduce it exactly, which is a very, very powerful tool in the time of this sort of so-called reproducibility crisis. Okay, so what are some benefits of containers? So longitudinal stability of software we've already talked about. So for example, upgrading Ubuntu 16.04 breaks FSL view, which is why they developed FSLIs or fossilize. Reproducible. In my previous example with the reproducing all of the code and the software, if I go in and change my image, for example, if I change one of the underlying software packages, it's no longer reproducible. So yes, containers can be reproducible, but if you change something about the container, it's no longer reproducible. As Stefan has mentioned, containers are portable, which is great, and they are isolated, so they're not exposed to the host system. On top of that, they're quite easy to use. So the example that I will give here is that if anybody here has tried to install ANTs, Advanced Normalization Tools, on the HPC or anywhere for that matter, it can be quite tricky without sudo access. When you're using containers, and particularly when you're using things like NeuroDocker, which we'll be talking about a bit later in the talk, it can be very, very easy to use and install software in a container. On top of that, some software is actually easier to use in containers. For example, fMRI Prep, MRI QC, and the BIDS apps and their integration can actually be very, very easy to use in containers, because there are all of this documentation that surrounds using it in the container. And if anybody's seen the fMRI Prep website or any of the BIDS apps websites, they would know that a lot of it runs really, really well within the container, rather than having to install SPM, AFNI, ANT, FreeSurfer, and all of the other Python tools that surround it, NiPipe as well, for example. So it can be really, really easy to use in these examples. So what are some challenges or some headaches that you can have? It can be hard to use at times, so it's a steep learning curve, and we will kind of see that in this talk. The syntax of the commands can be quite difficult as well. Docker generally won't work with high-performance computing systems, so if you have a HPC at your university, Docker generally won't be on there. As I said before, versioning of containers comes with no guarantees. Images may just disappear if I decide to remove my own image from my analysis pipeline. It's just gone, and there's nothing you can do about that. Things can just disappear or change. There are also licensing issues. So as many of you would know, for FreeSurfer, you need a license file in order to run it. The same with FSL, you need to actually sign a license in order to use it. MATLAB as well is also proprietary software, and the license is very expensive. You can run the MATLAB runtime within containers, but again, it does need a license for these other programs. The other challenge is mostly that it is a black box, so you don't really know what's inside the container when you use it. You can build a Singularity or Docker container on your computer and have no idea where it came from, who made it, or what's inside of it. So it's always good to check. And as we said before, the version of Singularity and Docker changes as well. Okay, so if there are any questions at this point, I would say not, because we're in the talk. So we'll just kind of continue on and say, how can we use containers? So in this section of the talk, we're going to be using the BIDS data structure, so brain imaging data structure, which you should be familiar by now if you're in the train track sessions. There was a BIDS talk, I believe. So BIDS, just quickly, and BIDS apps, neuroimaging tools and workflows in Docker containers, for example, FreeSurfer, SPM, etc. So all of these different tools run on the BIDS data format. So if your data is in BIDS, then you can easily run all of these tools and run all of these analysis pipelines very quickly. Okay, so we're going to be going through how to use containers at the moment. So the first one that we'll talk about is Hello World. So this is kind of an interactive type of session. So all of the code to this will be on the HackMD website, which we would have sent to you via email. It'll also be on the Mattermost channel. So the first one that we're going to be going through is the Hello World example, which is the easiest version. So if you have Docker installed on your local computer, you can simply type this command, which is docker run hello world. And hello world will show you that hello from Docker, this message shows your installation appears to be working correctly. So that's the simplest example of just running a Docker command. The next one that we'll be going through is just that Docker does cache these images. So what happened with the Hello World example is that Docker pulled a container called Hello World from Docker Hub, which is where all of these containers are stored. And it pulled it down into your computer. It's very, very small, only a few megabytes, I believe. And then what it did is run a program within Docker called Hello World, which printed that text to your screen. Once you try and rerun Hello World, it won't try and pull that container down again. So it already knows that you have the container. So this can be very useful if you're rebuilding containers with slightly different options, because it can actually cache the different parts of your container that are being built. Okay, if you want to show the images that you've downloaded. So in this case, we've got a few different Docker images in our system. Here we've got an Ubuntu, we've got Hello World here, which is the one that we just downloaded. And it's not even megabytes, it's a few kilobytes even. So what can end up happening is that it can fill up your computer quite quickly. And you can remove these, pardon me, you can remove these images if you want to. So in order to remove them, you can just use a command like docker rmi, which is remove image, and you can actually remove that Hello World example that we were just looking at before. So our Hello World one here, docker remove force is -f, Hello World, and what we end up doing is deleting that, that image from our computer. And then if you want to re-download it, you just run docker run or docker pull, the same as before. Okay, so now what we can see here is that that image is now gone. So it used to be down here, and now it's gone from our system. Okay, so the next one, which I would say is probably the most practical or useful example that most of you will want to use, is using fMRI prep. So as many of you will be aware, fMRI prep is a general purpose pre-processing pipeline that uses for fMRI data, that uses the best parts of many different tools. Maybe saying the best parts isn't a great way of saying it, but good parts from many different tools in order to make a sort of standardized pre-processing pipeline for fMRI data. So these are all of the different steps that are performed within fMRI prep, which includes outputting some confounds at the end, storing nuisance regressors. It's got the works. It's got everything in it. It's got free surfer reconstruction if you want that. It's got AFNI. It's got spatial normalization using SPM. It has everything. So there's about 6 or 7 different software programs that are actually used within fMRI prep. Now, if you wanted to use this normally, you would need to have free surfer, SPM, MATLAB, AFNI. You would need to have all of these different NiPipe dependencies installed as well. But with containers, they contain all of that software and all of the necessary components for it within a single image, which can then be run, which is quite powerful. So let's go through a quick example of how to run a Docker image of fMRI prep or Docker container for fMRI prep. So the first thing that you would need to do is, of course, download the container. And if you'd like to go to the fMRI prep website, you can see how to do that. But it's simply just docker pull direct lab fMRI prep latest, and that will pull the container for you. So the main command to kind of understand here is that you need to use docker run. And that's the main thing that we'll be going through today, is running the Docker image and including all of the different variables that you need in order to make fMRI prep run. So we won't be going through all of these different variables today because we want to keep it nice and simple. But if you do have any questions about what the different variables mean, how they work and how they interact with the container and the operating system, please ask on the Jitsi room or on the Zoom channel here. On any of the Mattermost channels as well. We're also on the help desk. You can see here that this is the name of the container. So after we've put a few of our different variables, we put the name of the container. And then these are the different parameters that you'd need to make fMRI prep run. So these ones here, for example, that's our data directory, our out directory, for example, and our work directory. Once we hit run and once we hit enter, what fMRI prep will do is actually run through the bids validator first to make sure our data is in bids, tell us a little summary of everything that's going on, and then it will start running fMRI prep version 20. So what we can see here is that it's running free surface subjects directory is here. And the really interesting thing here is that if I then kill this job and go outside of the container, and I try and run recon all outside of the container, I'll get an error thrown. Recon all, of course, being the reconstruct pipeline from FreeSurfer. So you can see that recon all isn't on my path and it isn't held anywhere within my computer, but it is within the container. So that means that I can run recon all and FreeSurfer from within the container, but I can't do it from without the container. Okay, so our next example here is pulling the image to a HPC, so a high performance computer. So here you are sharing all of your results from project to your friends after you've run all of that data on the HPC. So our next example, we've done our 1 participant, and now we want to do 100 participants on fMRI prep with our HPC to impress your boss. So Docker doesn't run, first of all, because the HPCs don't allow us to use Docker. So what we need to use is Singularity. Or we could install all of the software, which would just be dependency hell, basically. So what we want to do here is push, well, we can do one of two things here. We can either push our Docker image that we've just made to our Docker Hub and pull it on the HPC using Singularity, so you can run the software without root access. Or we can just pull the image directly from Docker Hub. And in this case, because we're using fMRI prep, what we're going to do is just build the image directly from Docker Hub using Singularity. So this may seem a little bit confusing at this point, and we kind of recognize that. So if you do get kind of mixed up between these two things, just kind of think about Singularity as the one that you're going to be using on the HPCs, and Docker is the one that you can use locally. And generally what I've found in my experience anyway is that I mostly use Singularity these days anyway, because you can build Docker images from Singularity. And that's exactly what we're doing here. So what we're doing is building a Singularity image, which we're going to be calling fMRI prep latest.singularity image. And we're going to be building that from this website. And what we can see is that's just telling us that it's Docker Hub, Poldrick Lab, fMRI prep, and latest. And then with that single command, after we've made our images directory, it will start the build and it will copy all of these different things. And we don't really need to worry about all of this different stuff that's happening. But at the end of it, it will actually complete the build with a file called fMRI prep latest.singularity image. And that Singularity image can be used in basically the same way as our Docker image from the last step. It can be used to run fMRI prep. So now we can actually do fMRI prep on the HPCs using Singularity, which is really, really powerful because now we can parallelize our jobs across hundreds of nodes or whatever your system is on your HPC. Great. So I think that's a good place for a pause, but we're going to be going on now to what a simple Docker container kind of looks like. So this next part of the talk, we're going to be going through how to actually make your own Docker containers. So if you're fine with just using Docker and Singularity for fMRI prep or other BIDS apps, this would be kind of the advanced section of the talk. But for those of you who want to do your own things and put your own software into your own Docker containers and Singularity containers, this is the section for you. Okay. So these slides and these code are all on the GitHub and also the HackMD site. So if you do get a bit lost, you can go through all of the code. It is a little bit, it can be a bit difficult to look through, but it's also all commented. And again, if you do have questions, feel free to ask us. So what we can see here is that this is VS Code. And when we do create a Docker file, which we just call Docker file, a cute little Docker whale appears as well. So we know that we've got a Docker image. And this is our headachy Docker file. So, oh, we've got a headache. So for this, I'm not going to go through the syntax of how to create your own Docker image. But what you do need to understand is that in order to make a Docker file, it needs to have the Docker format. It needs to have all of the different things that you want to include in your Docker image in different lines, on single lines even as well. And the syntax is all kind of readily available online if you want to have a look through how to create your own. We've got some examples on the GitHub as well. And we're going to be showing you how to simplify this with NeuroDocker in just a moment. So for the moment, this is kind of the structure of a Docker file. And what you want to do is you want to build that Docker file, right? So you want to create your own Docker image now after you've decided what type of software you want to put in it. So in our example on HackMD, what we use is ITK Snap. But in this example here, we're not going to go through exactly how we're doing it. But the point that we just here, so we can see build ITK Snap Docker, and the Docker file lives within that container, sorry, within that directory. And what we want to do is, in its simplest invocation, just use Docker build and point to the directory that contains the Docker file. And this may all just look like garbage, but it's actually building each step, which is each line from that Docker file. And it's doing it one by one and using the case for each time because we're already built in this case. Okay. So now that we've built our Docker container, and there are plenty of examples of how you can create your own Docker container, so we probably won't go into that in too much detail. But what we're going to try and do now is actually use the Docker container interactively. So we're going to go into the container. So we're entering the matrix here, guys. What we're going to do here is run a graphical application, which does require some wizardry using Docker, but we're just going to keep things simple and actually run the Docker container interactively by going inside of it. So what we can do now is actually enter inside the Docker container. So what we can see here is that we're sitting within my C users Thomas file, and then we go inside of the container, which is called ITK Snap, and that's the name of the container. Then we're inside of the container here in the next line. And then what we can do is simply run the command that we normally would after exporting our display variable, but don't worry about that too much. What we can find here is that when we run ITK Snap from inside the container, we get well, basically we can run ITK Snap, and it's a graphical application. So this is really cool because I don't have ITK Snap installed on my computer, but it is installed within the container. So then I can view images by using the container quite successfully. Yay. This would be another question slide. So if anybody has any questions at this point, I know that was probably a hard one to get through, but if you do have any questions, let us know. Okay, for those of you who tuned out because that was all too difficult, we're going to make it nice and simple for you now. So what we'd like to do now is distribute the pipeline that we've made or distribute our own software and do something a little bit more advanced, but use simple tools. So we don't want to actually create our own Docker. Well, we do want to create our own Docker container, but we don't want to have to write our own Docker definitions file for everything. So NeuroDocker is a project that helps building imaging pipelines in Docker, and by using this project called ReproNIM, Reproducible Neuroimaging. So what we want to do here is basically create our own Docker and Singularity definition files so that we can create our own software pipelines very, very easily. So this is just a screenshot from the NeuroDocker website. And what we can see here is that there's all of these different software packages that we can use and actually install within a Docker or Singularity container. So we've got SPM, NeuroDebian, Mmatrix, FSL, FreeCipher, all the rest of it. There's also NiPipe in there too. So using just a few simple commands with NeuroDocker, we can actually make our own Docker files and Singularity definition files in order to create our own bespoke Docker and Singularity images, which is really, really cool. So for those of you who just want to make a Singularity image with FreeSurfer and SSL on it so that they can do recon all. This is the part which is probably the most important bit. So here's what a, let's say we want to look at some images of brains. So we're going to generate a singularity recipe using NeuroDocker. And the exact commands for how to do this are again on the HackMD website. Don't worry about this, this is the output, but this is the input. So this is all we had to do in order to make all of this. So it's a NeuroDocker generate, and we want to make a singularity image. And what we might do here is, define the software that we wanted to use. So for example, in this case here, we wanted to use ITK Snap version 3.8, and then do a bunch of other stuff that might be important for making ITK Snap run. But here, NeuroDocker actually makes it really simple to create these types of definition files. So what's happened here is that with all of this, this short few lines of code, we've created all of this singularity definition file, and we can make a Docker file as well, so that we can build our own Docker files from NeuroDocker very, very easily with just a few lines of code. So for those of you who are just looking to make a really simple Docker file or a really simple singularity file, NeuroDocker is really a good place to start. Okay, so the last couple of things that we're just going to go through today are building singularity containers as well. So let's say that we just created our NeuroDocker image that has FreeSurfer on it, for example. We want to now use that FreeSurfer container on the HPC. So what we can do now is actually build that, that container on the HPC itself using the latest versions of Singularity. And what you actually do is build the container online and then pull it down into the HPC. So with just a few lines of code here, what we can do is take that Singularity file that we have created from NeuroDocker and use it on a high-performance computer or even on your own computer and build it remotely, which is quite useful if you want to make your own analysis pipelines with different bits of software from all over the place, or even your own software and your own data. And you can build it all online. Cool. So what you'd have to do is just follow along with the code that we've put online, but basically remote login to Singularity, create this API key is what it says here, just follow the instructions, it's super simple. And then what you can do is build your image using the Singularity ITK Snap Singularity definition file that you made with NeuroDocker. So your steps here would be create the NeuroDocker Singularity definition file and then build it remotely on the HPC, and then you're good to go. You've got your Singularity image that you can use, and it's got all of the different software that you required thanks to NeuroDocker. So it should be a fairly straightforward process. And yeah, if you do have any questions, of course, let us know.
Can I add two little things to this? If you quickly go back, I just wanted to, we don't have it in the slides, but there's two comments I want to make. So the first one is ITK Snap. We added this to NeuroDocker for this example. So if you're running NeuroDocker playing from the repository, ITK Snap might not yet be in there because it might not have been merged. So if you run into an error, the problem is we added that. The second thing is this remote building, as Tom said, is really, really cool. I ran into one problem yesterday where it said there's not enough storage available. And the thing is, if you have this problem, you can only build an image that's 11 gigabyte in size. So if you store images in your Singularity library online, and your library is basically already full, you can't build a new image. So it will not tell you that this is the problem. It will just tell, oh, you don't have image. You don't have any space for a new image. So I just wanted to say that because I noticed that yesterday, so we hadn't added to the slides, but I thought it's an interesting one.
So the image can only be under 11 gigabytes or 11
Correct.
gigabytes in total? Okay.
So exactly, so every image, exactly, the maximum size of an image is 11 gigabyte. And then if you keep your images in this library, you decrease this thing. So I had built multiple images, and I basically was filling up my storage online. And I didn't know that I have to delete them if I want more space. So I thought probably people run into the same problem. So I just mentioned it.
Definitely people will run into the same and many other problems, I'm sure. Okay. So yes, here we are, happy that we've got our singularity image. At this point, there'd be more questions, but we'll just move on. And I'll hand it back over to Stefan at this point, who'll be talking about transparent singularity.
Yeah, so that's basically now, if that was the advanced part, now we're going into a bit the geeky part. So when we started with using singularity for our analyses, we wondered, okay, do I now always have to type singularity, exec, ITK snap, something, ITK snap? Because I hate typing personally. So we thought, no, we should make something that makes this easier. So Tom and I were thinking about it, and we came up with let's just build a tool that automatically writes wrapper scripts around it, so that basically it ends up that you don't even have to type all the singularity stuff around it. So you just type IDK snap and it just works. So that was the goal. And that's how this project was born. And we call it transparent singularity because you feel that singularity is not even there. It just makes your stuff work on the HPC. So how does it work? So we'll just show a quick example. So in order to have it to work, you need to clone the transparent singularity repository, and then you already give it a folder name. So I'm just taking example FNI 20.106. So it will pull that thing, will create a folder. Then you cd into this folder, and then you can run the script. So we call it run transparent singularity. And then as the argument, you give it the container name. So there is a list of containers that we have made available already, but you can also just add your own container there. You just need to, you build your singularity file, you put it there, and then you just call that name. And then it will not try to pull it from our registry, but it will just use your local container. So, and when you run it, what it will say is I'm installing the container into your system. And for this stuff to work, you have to set up bind paths. So we described this in the repository. But after doing this, it will be really easy to use. So what it has done now is it has created for every binary that's on a certain path. So that's why we had in the recipe that we showed earlier, we had this variable that we call it deploy path. So we introduced that in order to make transparent singularity work. So it basically looks at the deploy path, and you can have multiple deploy paths. It will look for executables inside the image. And what it will do is it will automatically create a shell script for every executable in the image. So, and these wrapper scripts are very simple. They will basically say, okay, I want to work in the current directory, and I want to call singularity. I want to execute this. I want to work in my current directory. Then I want to call a certain container, and then I want to call a certain command in there. And I want to pass on all arguments that I gave this thing. So also what we do in addition is we create a module. So lots of HPCs use the LMOD module system. And when you then hit module avail and you have your module path set up to the folder where we created these modules, you see suddenly, oh, now I have FNI and FreeSurfer in your module system. So you can extend your own HPC with your own modules, and everything runs from inside the containers. So the beauty of it is now when you run module load FNI, you get FNI on your path, and then you don't have to type singularity or anything. You just type summa, and the viewer of FNI will just open, and if you're lucky, it will show you Humor Simpson. If not, it will just show you a plane or other things. So it always starts with random thing, but it shows that we can run graphical applications. Again, we actually logged in remotely into HPC, and we just have mobile XM, which provides a local an X server, and we can actually render stuff on our Windows system. And now we can just continue using NiPipe without actually changing anything in NiPipe, because it feels for NiPipe like if these tools would be installed natively. And because we combine with the module system, you always are in control of what containers you want on your path and what you don't. So we're using this since, I think, 2 years now, and we're pretty happy with it. And for us, it just made our life a lot easier, because what this basically allows you to do is you can start with your analysis locally on your computer, then you move to a bigger workstation, then you upgrade your workstation, and then you move to different HPCs. And everything is very, very movable, very portable. And this is pretty much what we had planned for today. So I think we thank everyone for their attention, and now we're looking forward to questions in the question and answer. Thank you.
Thanks.
Hi everyone, my name is Michael Dayan. I am from the Foundation Campus Biotech Geneva in Switzerland. So I'm very happy to be here today to present this introduction to machine learning with scikit-learn and NaiLearn for the application to neuroimaging. So first of all, I would like to congratulate the OHBM Brainhack committee for pulling that off remotely. And special thanks also to Lisa and Remy for organizing this training session and for the invitation. Thanks a lot. So this, the content of this session is on GitHub here. So I guess you already have the Jupyter notebook and the data, but if not, you can quickly get them at this link. So I will present both an introduction theoretical to machine learning, just an overview, and then we'll see the application with sklearn and NaiLearn. These packages are all written in Python, and they are embedded in a very strong community of open source software. And what is particularly amazing with these packages is that they have an excellent documentation with very rich examples, which are very well made. And actually, there were a few talks during the NaiLearn days a few weeks ago with Gaël Varrocco, Bertrand Thirion, Elisabeth Dupré, who was core developers of NaiLearn. And they explained that it was actually the way they code is documentation driven development. So they really put the user at the center, thinking ahead of what would be needed to be able to start using the packages. The examples are very well made, and that's why I'm going now to present an overview of machine learning and the framework, typical framework of scikit-learn, but I'm not going to go into details in the machine learning algorithm, especially considering we have 90 minutes and it will be already quite busy. And for those who are in EEG, because NaiLearn is more focused on MRI, for those who are in EEG, there is also the MNE package, which has the same mindset. So example driven for easy access by the users to the package with very well-made examples as well. And it's not a coincidence because the core developers actually overlap in between these different packages. Many are from in area. Okay, so let's start. So before going into the machine learning details, I often like to take a step back, and so I would like to have an understanding of why machine learning is useful for scientific research, at least some aspects of it. I would say that one of the core hallmark of science is to have testable predictions. So, for example, for Aristotle's theory of gravity, his theory was that objects fall at a speed proportional to their mass. So if you take two objects, the one which weighs 10 times more than the other will fall 10 times faster. Galileo's theory, in contrast, was that the objects fall at the same speed. So obviously you know which theory could be tested to be right. And one experiment was done actually just a few years before Galileo's in Netherlands, showing that two objects of different weights actually fall at the same speed, and there is not much friction. And another fundamental aspect of science is generalization. So you want findings to apply in other contexts, at least in other experiments than your own. And obviously Galileo's law was found in to be true in many different contexts, including in the moon. So there was David Scott as part of the Apollo 15 mission who reproduced this experiment with a feather and a hammer. And he shows that they actually fall at the same speed. So now let's keep with this falling objects idea, and I would like you to do a thought experiment. So imagine you are still in this 17th, 18th century period, and at this time the problem of shooting weights objects was really a big issue to solve. So imagine you are a scientist at the time, working at university, and to make ends meet as a side job, the only thing you could find was to throw cannonballs with cannons. Maybe you look like more the picture on the right in the 18th century. And your mission was to try to predict the range of the cannonball according to the angle of the cannon. And that was actually not easy at all, because at the time there was still Aristotle's idea of trajectory in every scientist's mind. And this idea was that cannonball would just shoot straight and then suddenly fall on a straight line, a bit like the coyote in Roadrunner. So obviously with this scientist's idea, it was very hard to predict if you could hit the target according to the angle of your cannon. So there was some efforts towards the end of the 18th century to have this table, to be able to have some ideas of if you were going to hit or not according to which angle you should choose. But there was not really any good model. So to do your mission, you actually need three things. You need to take measurements, to find a way to make predictions, and to assess the generalizability of your prediction. So to know how much your prediction will vary in different situations for new data sets. So let's start with the measurements. So typically what you will need is a set of observations, also called data points, samples, or examples. And in this case, it will be shots. And with these shots, you will need a set of features. So features is a characteristic of your observations, like the angle psi of the cannon, the initial speed of the cannonball, its mass, its radius, etc., etc. And then you want to predict if it hits the target at, for example, 100 meters. And that's your outcomes. They are called labels. And all this information is a data set. So you need a data set of observations. These observations are characterized by features, and you measured your desired outcomes that you want to predict later, which is if it hit your target or not. So actually, the choice of outcomes and features is extremely important and is really fully part of your research design. So in our field, typically the observations could be the subjects, and the features will be characteristic of the subjects and the experiment. So the age, sex, maybe some values in the region of interest in the brain, so RI1, 2, etc. And the outcomes could be if the subject has a disease or not, or if he's a normal control. But you really have to think of what your outcome should be. Actually, 10 years ago, there was this initiative, the Research Domain Criteria Initiative by the National Institute of Mental Health, who tried to push for a different approach. So instead of having this binary diagnostic outcome, trying to have something else, because this binary outcome can actually impair the understanding of the disease if all the research studies are too much focused on this approach. Because people with the same diagnostic can actually have very different symptoms, and people with given symptoms can be likely to have an additional disorder, which will not be even considered. And the difficulty of having a clear diagnosis may actually cause researchers to exclude patients because they will not fit the gold standard of the diagnosis criteria. Actually, this criteria can be quite arbitrary sometimes. So the idea is really to choose, instead of this binary outcome, to choose biological, physiological, and behavioral dimensions. And in this way, you can explain different diseases with the same outcome. They are more general, and you can better understand the link between your neuroimaging biomarkers and the disease or other diseases. So in a case, for example, instead of having as outcome if we hit our desired target at 100 meters, a better outcome could be the range, because this way you could generalize to different situations and better understand your system. Okay, and now we need to find a way to make predictions. So imagine your original dataset is this one. So it's not a trajectory, is on the x-axis you have your experiment angle, Canon angle, and on the y-axis you have the range, so how far your cannonball went. For example, for around 48 degrees, it went 75 meters. So if you have this dataset, you have different model, for example, you could propose. You have just a straight line. You could have a parabola, so a polynomial of degree 2. You could have even a polynomial of degree 5. And all these models, they match your training data, your data set, I mean. So the question is which one to choose. So we have to find the least bad model, let's say. So we have to define what is bad. So bad is the error you make. So this error, you can measure it simply by looking at the difference between your dataset and what your model will predict for this dataset. So let's zoom in to understand it more clearly. Imagine you have this data point x3 here. So for this point, the error will be the difference between what your model will have predicted for this data point and what your dataset actually is. That's your error term. So then your total error, how do you define it? So if you just sum the errors for each data points, there will be a problem because you have both positive and negative errors. So they will kind of partially cancel out. So you could take the absolute value of all these errors, and that's actually the absolute error. It's called the absolute error. Or you could take the squared error, which has nicer properties. So you just sum all these squares, and for your error not to depend not to depend on the number of data points you have, you take the mean, and that's your mean squared error. A very common metric used in machine learning. So to have the least bad model, you need to have the least mean squared error. Okay. So the equation of this line is just a simple line depending on the angle psi of the cannon and the range r. So you have these measures, but what you want to compute is these two parameters here, the intercept and the slope. That's your two betas. So how do you compute them, these parameters of your model? So there is a general approach in machine learning which consists in using the derivative. So here you have your error function, actually it's called your loss function, and you want to find the minimum. What is the parameter beta psi, which will give you the minimum error. So you know that the derivative gives you the direction of your curve, and the gradient will indicate the increasing values, and by taking the negative gradient, you can go towards the minimum. So you just do that iteratively. So you can see here that the curve, you start from any random point, and you just follow the direction of minimum error to arrive at the global minimum. And then that's it. You have your model is trained, you have fitted your model, it means you have found the two parameters. And this method of least square error was actually already used at the end of the 18th century. That's why we set this problem at that time. It was used by Legendre and Gauss, who was just 18. And actually Legendre was a professor in ballistics. So it's also fit in this problem. So that's why I chose this theme. So now your final mean square error is this number. So that's the performance of your model on the data set you have, on the training data set. So in case you have two parameters, for example, for the parabola, the error function, the loss function will have this kind of shape, and it will be exactly the same principle. You start at a random point, and you just follow the opposite of the gradient to go down. So it's a gradient descent. Okay, so again, so we have these three models. So this one is only two parameters. We know the mean square error. The parabola with three parameters, one more parameter for the psi squared angle, and a polynomial of degree 5. So the question again is which one to choose. So if you look at the mean square error of each model, you can see that it's this one which is closest to the dataset. But is it enough to decide which one is the best model? Obviously, you feel it's a strange model to use. What you really want to know is how this model will perform on new data, on unseen data. So a way to do that is one way, if you have access to a new data set, you just use a model you just fitted and you apply it to the new data. So you take the angle psi, you put it in your model, and you predict your range. And that gives you a vector y. And you just compare this vector y with the measurements, the true measurements you had. By comparing the two, your prediction with what was measured in this new data set, you can have again a performance score, a test score, again with a mean square error, for example. So the error, the sum of square difference between these two measures, and that will help you understand how good is your model for new data. So in this case, you can see that for this new data set here, this model, the polynomial of degree 5, the error is massive. So it didn't generalize well at all. The linear fit is, the error is is worse, but it's relatively reasonable. Whereas this parabola is almost the same error, even a bit lower, maybe due to noise, but it's almost the same performance. So yeah, it's very important to assess the generalizability of your predictions. And here you can see question is also how variable is your model. If you have a new training, if you have a new data set and you fit again your model, is it going to change all the time or is it going to stay constant? And this is a very important question. It's a fundamental concept actually in machine learning called the bias variance trade-off. So if we look at data points, let's say 40-degree angle, we want to know every time we fit a different model, is the prediction going to change a lot or not? So knowing the ground truth is around 75 meters for this angle here. For each model here, I simulated 1,000 data sets and look at how the prediction change. And you can see that for the straight line, actually, so on average, there was a systematic error compared to the ground truth, but the variability was not that big. In contrast, so one with degree 5 had a very high variability, although on average, it has almost the ground truth. And the parabola was in the right in the middle, so you had reduced variance, but on average was also very close to the ground truth. And that's exactly the bias variance trade-off. So the total error is the sum of the variance and the bias, and it's a trade-off. So models with relatively low variance has a high bias. It means even with an infinite number of data points, it will be far from the true function. In contrast, with infinite data points, this highly variable model will fit perfectly the true function. But when you have a limited number of data points, it will vary a lot. And what you really want to do is to be in between. So to have a low bias, low systematic error, but also a low variance. And that's all the goal of machine learning practitioners, to choose the right model with this kind of optimum trade-off. And you can see that the variance is directly linked to the model complexity. So the more parameters you have, the more closely is going to fit your training data, but the worse is going to be on unseen data, on test data. And when you increase complexity, you also reduce the interpretability of your model. It's harder to interpret. So it's really, better to have a low complexity model, which also is not much variable. So this bias variance trade-off is often represented as this kind of target, since that's from the Elements of Statistical Learning book by Hastie. But typically either you have a high variance with a low bias, or you have a high bias with low variance. If you have high variance and high bias, there may be a problem with your model. That's for sure. You really need to do something else. And if you have low bias and low variance, you may also double check your results to check you indeed have a very good targeted solution. So to make a very simplistic analogy, maybe for humans, it's if you consider someone having having opinions on a topic which change every day depending on which person she or he met, we can say it has a high variance. But in contrast, if you have someone who is very conservative in his opinion on a given topic, she or he will have high bias and low variance if they never change their opinions. So in between will be to consider new data, to change or representation of the topic to be able to have a better, more accurate representation. Okay, so time to practice. So let's go on the Jupyter Notebook to be able to analyze the data. So the first thing you will have to do, if you didn't do it already, is to download the data with the following commands. But it's much better if you open a new notebook for that, because the time it's downloading, you won't be able to execute the next cells. So if you could open a new notebook, that would be much easier. You open the new notebook, you run these commands, and you keep a notebook to follow along the commands we are going to run now. Okay, so I'm not going to download them because obviously I have them. So we'll start with a simple regression model. So the range of the Canon angle we're going to investigate are between 20 and 60 degrees. And we are going to get simulated data already generated. So if you use a GitHub repository, you can find the datasets here. So we are just going to read the CSV file with pandas. So you have other cells I'm not showing here, but which is on the notebook to import pandas as PD. And we are going to read all our data in this one and take a light version just for plotting. So this command, this function is actually from the Python file also in the GitHub repo, which is simply to extract interspread data, just a small subset for plotting. Okay. So we are going to generate a single data set of 50 observations. So the data generated includes 100,000 samples. The idea is just to take one. So we'll initialize a random seed to be able to reproduce our experiment. If you want, you can change it to see how your results will differ from what I'm showing. That could be interesting. And so we're going to extract one dataset of 50 sample, 50 observations with this range of angle. So let's explore our dataset. So I need to run the commands, otherwise it's not going to work. Okay. So yeah, we're only interested in looking at a range of angle, and our datasets look like this. So we're going to ignore these true values, and we are only interested in this experimental angle measured on experimental range. So we're going to plot the datasets to have a better idea of what we have here. So that's our 50 data points. So here on the x-axis you see the angle, on the y-axis the range. So the idea is to find how to find the best model which according to our data. So for this purpose, we are going to split our data into a training set to fit a model, and then a test set to see which one is best. So we'll compare three models, the same ones as we saw in the slides. So standard linear model with two parameters, intercept and slope. The parabola, it's a polynomial of degree 2, sorry, with three parameters, intercept, slope, and this beta coefficient for the chi-square term, and a polynomial with of degree 5. So it has six features, and so 5 features, and so 6 parameters because of these intercepts. So scikit-learn, sklearn has lots of very useful functions to facilitate your job. So instead of writing lots of commands, you have lots of utility functions. So this one, train test split, is once you give a dataset, here you have some documentation if you want to look at the detail, you will be able to split them into training and testing sets. So just to explain better, so our feature matrix X has only one column because we only have one feature, but if we add several features, we'll have all of them here. But in this case, we have only one feature. So that's our matrix X of features. And our matrix on our outcome is a single vector with all the values. In this case, that's the range. So from this set of features, we want to predict the range. And the train test split, simply take as inputs your X matrix and Y vector, and you just have to give the size you want for your test datasets. So in this case, it's 40%. So the size of your testing dataset will be 40%. And it's going to take that randomly. So you need to give a seed. I mean, if you want to reproduce your result, you can give a seed. So since we have 50 samples, and if we take 40%, that will be 20. We have 20 samples in our test side, and the rest 30 in our training. So we can check that by looking at the length of the X train and the X test generated. Yeah, it will be 30 for training and 20 for testing. And it will also generate the labels for training and the labels for testing. So even if it's a continuous measure, it's called a label. Okay. Yeah, let's have a look at X-train. So you can see it's all my experimental angle, but there are only 30 of them instead of 50. So let's train our model. So in this case, from all the linear models of scikit-learn, you can see they have many different ones. We'll import the linear regression one. And to be able to estimate the performance, we need a different scoring function. In this case, we'll use the mean square error and the R2. So it's the traditional correlation coefficient squared. Okay. So every time in sklearn, there is the same approach. And once you know how to use this approach, so seeing it only once, for example, with a linear regression, will be really helpful because you can apply almost exactly the same workflow to a different estimator, to a different model. So the way you do it is that you instantiate a model which is actually an object. So every model is an object. So I guess most of you are familiar with object-oriented programming, but once you instantiate this model, so here I call it LM, you will have function and attributes. So methods and attributes. So let's see right now what does it entail. So in Python, you can access these methods and attributes just by putting a point following objects. And here I can see I can fit, I can get the parameters of the model. The parameters actually, it's not the parameters, the betas, but it's more like the hyperparameters normally. I can check. Yes. So that's really, it's more like hyperparameters as we're going to see. What else? I can fit and predict. And that will be the main function we're going to use. So here, actually, we'll fit, so our train observations to our labels. And actually, we don't need to have the output saved into new variables, because internally, when you call that, is going to change the internal objects in this LM object. So the internal state, I mean. So now you can see there are new things inside this instance, including the coefficients. And that's actually the coefficient of your model. And here you just have one for the slope, and the intercept, actually it's in the intercept attribute. And what's interesting in scikit-learn is to differentiate what has been fitted. There is an underscore at the end of the attributes. So just to recap, I had I instantiated an instance from an object, from an estimator. Then it was empty. Then I fitted from this instance, and it changed the internal state. And now I have the different coefficients as well as the intercepts of this model. So I can actually print them, and you can see the intercepts and coefficients. So that's the two parameters of my model. Okay, so now we want to use predictions to compute the performance of our model on the trained data and also on the test data. So just to show you how you use a predict function, you just give them, you can give a list of several features. So here, if I had 2 features on my feature matrix, to do prediction, I will need a data with two features as well. And here it's just a list of prediction. But in this case, I need only 1 feature. So I ask, can you predict me the outcome for this observation, that observation, and that one? So in this case, it will just give me 3 predictions for each of these different sets of features. And so the training score can provide an idea of the performance of the model. So it's very simple. Again, we just call the predict method of this LM object first on our training data, because we first want to know how well the model does on the data we just trained. So it should be kind of best possible outcome for the test data. You can very rarely do better than what you do on the training data. It will be like kind of an upper bound of performance if you want. So we predict the outcome from our training data, and then to obtain the performance, we use the R2 score between the true values, so that's the Y data in your training, and what we predicted. So if you remember, we need to compare the two to obtain the performance inside the training data. And we'll also compute the mean square error. So in this case, we see that the R2 is average, and we have the mean square error. What we really want to do is compare that with the test data. Yes, and your object actually have a score function, which will give you the R2 by default. So you can also use that to get the R2. That's the same thing. So we'll save them. We'll save all those scores to have a plot at the end to be able to compare the models. And in this case, since for the mean square error, the lower is better, not to have plots going in all directions, I will take the negative mean square error. So that's the greater the better, like R2. It will be simpler to compare all the different metrics, performance metrics. Okay, so the most useful and what you really want to know is how good is your model on unseen data. So there are many different scores. Here I'm just looking at the mean square error and the R2, but you can see here all the different scoring function you have. So let's do it. So in this time, we fitted a model. If you remember, we fitted a model on the training data, and now we are just going to use it to predict this new data. And we are going to compare our prediction with the true values, which are the Y for the test set. So normally the R2 should be lower and the mean square error higher, because it should be worse on unseen data. And indeed, it's quite worse. We again save our results for the future plots. And now let's do exactly the same thing, but for the polynomial of degree 2. So the way it works for polynomial models is you just need to create your features, so different powers of your features, and then add it to a standard linear regression model. So you need 2 steps. First, we need to create the polynomial features here. I will call it polytransformer. Again, it's an object with methods and attributes. And I will call another linear regression model. I'm just going to call it differently to differentiate it from the previous model. So don't forget to run everything. Okay. So again, that's the same thing I just said. First, you transform your features, and then you fit the linear regression on the transform feature. So here we'll transform our features. Actually, we can look at what X-train was before and what it is now. So you can see that first you had only 1 features, and now for a polynomial of degree 3, you have 3 for each degree. Degree 0, so constant. Degree 1 is the same as the original feature, and degree 2, so the your features power 2. And we're going to fit. So this time we fit our transform features. And we can look at our coefficients. So now, since we have 3 features, we have 3 coefficients. And 0 is for the constant term. We have an intercept. Here. We have the intercept. So there is the degree 0 term is not used. Let's compute the training scores as before. We just predict what our model will do on the training data and compare with the ground truth. Okay, so we have a quite high R2 in this case, and a low mean square error. And we'll save the results again with a negative of the mean square error. And now always the most interesting, how well it does on unseen data. So it's very important to remember you again have to transform your test data to have 3 features. So in this case, you may wonder why we called fit transform. So there are often 3 different methods for different purposes. There is fit, which is going to kind of compute the parameters needed to do the transform, and then you do the transform. But you can do both at once by doing fit transform, and that's what we do here, 2 steps in 1. So we're going to transform our features and then use the model which has been fitted on the training data to predict unseen data. And we compare that to the ground truth. So this time the ground truth is Y test. And it should be worse. So, but in this case, very surprisingly, it's the same. So that's the best case scenario. When you fit your model on training data, on unseen data, at best, in the best case, it's just going to do as good as what you do on your training. And actually, that's the case here. Again, we're going to save the results to plot them later. And last thing, we're going to do the same thing, but I will introduce you to something extremely useful in scikit-learn, which is a pipeline object. A pipeline will allow to connect your different steps together to avoid to have them to do it again at training, again at testing, etc., etc. And it's very common to use because often you have pre-processing steps. You don't want to have to repeat every time you reuse your estimator. Okay, so you already know what the pipeline is, because it's exactly the same as the degree 2 estimator. And what's very convenient is once you have built your pipeline object, you can use the same method fit predict, except it's going to do all the pre-processing steps. In this case, it will do the transformation into features at different powers, and then call the fit method of your estimator, which is a linear model. It will do all for you in one call. So you just call pipeline with a list of steps. You give them a name, and then you put the objects of the step to implement. So in this case, we call it polytransformer, and we'll do the polynomial features transformation with a degree 5. And then we'll use our linear regression model. So it's just a list of tuple with the name you want and the actual objects. And once you have created this pipeline, you just can consider it as a normal estimator, as if it was your linear regression, except it's going to implement all the steps you put in the pipeline. So we'll just fit our training data, model to the training data. And now we can look at our coefficients. So this time there are 3, 4, 5, 6. Again, 0 here because there is an intercept. So this feature to the power 0 is not used. We're going to have the get the performance on the training datasets by comparing, getting the prediction for the training and compare it with the ground truth. Okay, so it's quite better R squared than the one before, but it's on the training data, remember? And now we're going to apply it to the test data. So what's great with the pipeline here, you can see we don't need to do any transformation because here, this one is a pipeline, and when you call predict, it's going to call automatically the transformation on this one, and then call the predict method of our linear model. So that's what's super convenient with the pipelines. So we'll have a prediction, and we'll compare it with the ground truth for the test. So as we know, the degree 5 polynomial is highly variable. On unseen data, the performance should be quite lower than the training. And in this case, well, it's quite lower, but not that much. So it did relatively well. So that's it. We can plot all our results. So I'm just using turning the list of dictionaries into a data frame and plot the results. Okay, so here we are. So here you can see the training score in blue and the testing score in orange, and it's always worse. I mean, that's to be expected. And what's quite impressive is that for the parabola, for the degree 2 polynomial, it did almost as well on both. And same for the mean square error. So remember, I took the negative, so higher is better. And you can see, again, it's better on the training than on the testing. And for the parabola, it's even better on testing, which is mostly due to noise in the dataset. So that's it. You saw the principal elements in sklearn, the main, let's say, functions. So using the fit and predict methods, and also how to score your model. And you also saw the pipeline object, which is extremely useful for including pre-processing steps, including transformations, for example. So now we'll go back to the slides to understand better how to estimate the generalization of a model. So the question now is how to assess the generalizability of our predictions. So as we said earlier, a hallmark of science is generalization. We want to derive findings that also apply to other experiments. So as the philosopher of science Karl Popper said, non-reproducible single occurrences are of no significance to science. Although I'm not sure what was his thoughts on the Big Bang. But in any case, when we apply that to our field, we want to derive neuroimaging findings that apply to other population samples. So when we study a sample, our findings, when we take all the samples from the same population, should apply as well. So it's very important to be able to assess how generalizable is our methods or findings. So in the case of machine learning, the workflow is typically to pre-process the data and then to split our data into training and testing to evaluate what is the performance of our estimator, of our model on unseen data. So should we select a model by testing several models on the training datasets and then applying on the testing datasets? Actually, we cannot do that because if you test many models, just by chance, one will perform well on the test sets, and it will not mean much because it can really be due to chance. So the way you do it is really you do your model selection only on the training set. The test set should be completely untouched, and that's actually how different models are evaluated. When you look at Kaggle, which is a website for competition in machine learning, they always keep a test dataset on their servers, and the best model will be evaluated without having ever seen the test dataset, obviously. And so participants have all the training set, but they don't see the test datasets. That's similarly for one of the dream challenges and trying to detect breast cancer on mammograms. There was a big $1 million prize, and the test dataset was obviously kept while all the different teams worked on the training dataset to try to improve the models. And in the biomedical imaging field, we have this MICAI conference, which has been at the forefront of this kind of machine learning challenges. I think one of the first challenge of the kind was by MICAI in the 90s for brain registration. And you have many challenges every year where you have to train your model and then the best models are evaluated on the test dataset, which is on the server. So obviously it's not a perfect system. For example, just changing a few samples in the test dataset can change the outcome. The scoring matrix chosen can also influence the results, but I mean, there's still a good system to evaluate methods, machine learning models. So you need to do the model selection really only within the training set. So how do you do it? You could split the training set into another training set and testing set we could also call validation. So we'll use the term validation and testing set interchangeably, but sometimes it's called validation set when it's internal. And we can do that, but that's not the best way. The best way is to use what's called cross-validation. So the approach is to split your training set into equal parts called folds. In this case, it's 5-fold cross-validation because we split it in 5 parts. One of these parts will be the test dataset, and all the rest is training. You just repeat that again and again to have 5 scores. So once you have these 5 scores, you can evaluate the generalizability of your model because you will get the mean score together with the confidence interval of this score. And this will be done every time on unseen data because you only train on the trained parts and you test it on unseen data. So let's practice this. So now we are back to our Jupyter notebook and we'll use cross-validation. So in this case, we'll import kfold. How does kfold work? You just give the number of splits you want, so number of folds you want, your data arrays, and you say if you want your data to be shuffled or not. Sometimes you have the data in order, in some order, I don't know, by age or And it's very important to shuffle the data to make sure in each fold they are independent. And in case you use shuffling, then you can use seed to make sure you will obtain the same folds if you want to reproduce your results. Okay. So just for you to understand better, we'll just use a toy dataset. I'm just taking 10 random ints between 0 and 1000, and we'll see, so that's it, and we'll see what k-fold will do on this one. So I will do 5 splits on these 10 observations, and here you can see what it returns. So the k-fold will return indices for your training and your testing. So it's a 5-fold k-fold cross-validation. On your indices, you can see the first 2 components of your data will be used for testing in the first fold, and then the rest for training. Then it will take the 2 successive elements for testing and the rest for training, etc. So in turn, it selects testing folds, and every time all the rest is for training. You can see there is no overlap in the testing indices and no overlap between the training and the testing. Okay. And now if I use shuffle, you can see that it will be random for the testing indices and training indices. So there is no order as there was here, in case your original data is not is ordered. You will need to remove this ordering for all the folds to be independent. So in our case, so here, just to confirm the size, if we use 5 split, let me see. Yes, we'll use a 5-fold cross-validation, and we'll compare different models. So we compare as before our linear regression together with the 2 pop line with the transformation on the polynomial. Okay. So I will just, so what I'm doing here is cross-validation of the different models. So I'm calling here the k-folds, 10 splits, so it's 10-fold cross-validation. And for each one, that's the index of the fold, and that's the training and testing indices. For each one, I will call my model, it's a dictionary here, you can see. So if I take the keys of the dictionary, that's the name of the model. And here I will call my model and call the fit function. And I'm calling the fit function on what? On the training data with the indices given by the k-fold generator. And every time I will fit the training to have a training performance score, I will predict the training to have this score on training and predict the testing fold to have the testing performance. And it will be done 5 times. So for each model, I will have the mean and the confidence interval of the prediction. So let's do it. Up. Okay. We'll plot the results. And here we are. So that's the results for each of the 10-fold. And you can see that often the testing is worse than the training, except it's not always the case, but sometimes it's very bad. You can see you have a negative R2. Negative R2, it means the variance explained by your model is worse than the model, which is just the constant mean of your observation. Degree 2 is doing actually quite well on the testing set. Whereas for degree 5, yeah, it can be pretty bad on the testing. And that's for the mean. For the median, for the box plot, we can see the spread of our scores across the 10 folds. And you can see that for the linear model, it's very bad, as the R2 on the testing. It's always worse, as I was saying, for the degree 2 and degree 5. But degree 2, here we can see a zoom of the same plots. Here, for the degree 2 is slightly better, and there is less variance. You can see again, the training is better for the degree 5, but for the testing, it's worse. But that's really the testing score, which is important. So again, we have confirmation that the parabola is better. Now, we know that sklearn has lots of these utility functions, and many are there to automate many of the operations. So instead of having this loop when we create the folds manually and compute the training and testing score, we have this cross-val score function, which do everything for us. So how does it work? You just have to get some metrics. The only additional step you have is to create a scorer. So you cannot give just the name of the metric or the function to compute the score. You need to call this make scorer function with a scoring function, and it will create a scorer that will pass to cross-val score. So it may not be super clear, so we are going to do it now. See what arguments it requires. We can see that you just give your estimator, the X, the Y, your scorers, and that's it. And it will do everything for you. For the CV, by default, I think it's 5 or 10, but you can also give it your cross-validation object, and it will do everything automatically. So let's see how it works. Here I have, again, all my models. And here I just have to loop on my models and call cross-val score with a model, my training data, my k-fold objects, and the name of the scorer I want. And jobs equal -1, it means I'm using all the CPUs to do this. And it's very useful because for cross-validation, you can parallelize everything because the computation of the folds are independent. So that's super useful. And then I put all the results in a data frame. Let's do it. Okay, let's plot the results. And here, you see how much easier it is. I just call cross-val score. I put the results in the data frame, and I just have to do the box plot. You have the confirmation that for testing, here the mean square error is much better than LM for the degree 2, but it's also it has less variance than the degree 5. And if you want to do even less code, you can use cross-validate, which can use not only several metrics, but it will also return the train and test score. The previous one only returns the test score. So it's the same pipeline. I call cross-validate with a list of scoring function. And this time, oops, I can have the same kind of plot as before, where I have the training and testing, but instead of doing a manual loop, it's just a few lines of code. Okay, we'll go back to the presentation to go to our next chapter. So this is the last chapter before going into real neuroimaging data. So the question is how to prevent overfitting. So one way to do it with linear regression is with regularization on other models, but we're going to see it for linear models. So if you remember this plot of trade-off between bias and variance, you can see the variance is characterized by a high variability in the models, depending on training data. And what you can do, because this variance is directly related to the model complexity, which can be caused by the number of parameters of your model, you can reduce the number of parameters. And you can do that with feature selection. It means you remove some of your features before training your model. Another way is to do regularization. So in this case, we can force the model's parameters to be 0 or to be small, because if they are big, your model is going to vary a lot according to the data. So by having them small, you can regularize them. You can make it being more stable. So if you remember this loss function, in case you have two beta parameters, two parameters for your model, if you look at the projection here, we can see this projection on this plane here. So the more away you are from the minimum, the higher the value of the projected loss function. So here we can see the different values. So what you do with regularization in this case is that even though your true minimum is here, you can constrain your parameters to be only in this area, for them to be small or 0. So the way you do it is that in your loss function, in addition to the usual term, you just add a penalty term so that the higher the weight, the higher will be your loss function. So if you want to reduce your loss function, you will need to reduce these parameters. And here is you just have one parameter, one hyperparameter to set it, and the higher this penalty parameter is, the more reduced or the more zeroed elements you will have. So you have two kinds of terms, either squared or absolute value. So with absolute value, it's the lasso terms. In this case, you can see that this constraint will look like this. And when your loss function meets the first allowed value, it will tend to be very small or 0, more likely 0 with lasso. But with ridge regression, this penalty term is squared, so it will have this shape. In this case, it will just reduce the betas. Okay, so with lasso, because they meet, this loss function is more likely to meet the intersection with x or y axis, they're more likely to be 0. So it's a great way to reduce the complexity of your model and so to bring it closer to this optimum position. So lambda is called an hyperparameter and is not fitted. You can consider that for a given lambda, you have a given model, and different lambdas, different models. So you need another procedure to find the best value. So let's see a way to do it. So one way to do it, for example, you could try to repeat cross-validation for each possible lambda and then compare your models. The problem with this approach is the same as before, because you will compare them. If you compare many different values, you will just obtain a much too optimistic performance score, because it will be the best one after many trials. So one solution to that is to use nested cross-validation. Nested, it means you're going to do cross-validation within your cross-validation. So here you try your 3 different parameters, you get the best one, and you test it. And you do that again and again, and this way you will have 5 different evaluations of your parameters. First, every time you can not only see which parameter is chosen, is it always the same one, and what will be the score on unseen data. So you have an estimation of the performance of your model. You can also check if it's stable, because if you have a different answer of the best model in each of these nested cross-validation folds, you will know it's unstable. So we'll have a look at an application in neuroimaging data. So here we are. Okay, so in this example, we'll try both feature selection that you mentioned and penalize regression with lasso. So I already mentioned what is feature selection useful for, is to help prevent overfitting and obtain a simpler model. So also called parsimonious, because you have a simple model, it's much easier to interpret, and if you have fewer features, the calculation are faster too. So we'll use a notebook, which was actually, it's an example presented by Jack Vogel at Brainhack School. So the machine learning approach is quite different, but the nailearn part is quite similar, very similar. So first we get the data. So normally you have already fetched them at the beginning of the session, as I was mentioning. And from the GitHub repo you got, normally this notebook is, the dataset folder is in the same folder as your Jupyter notebook. So normally this path, you don't have to do anything. Sorry, this one is for fetching the data. Voila, here, the offline directory is inside what you downloaded from GitHub. So we'll just use this one. Okay. And we'll also use the phenotype file. So this, actually, this file is to have the connectivity matrices. I'm going to explain in a bit what is it. But first, I'm just going to get this data. So the data is in two parts. We are going to try to predict age from brain connectivity. So this X file is actually features of connectivity we're going to see in the nailearn section, which characterize the connectivity in the brain with functional MRI. And what we are going to predict is age, and age is within this phenotype file. So for each subject, we have different values, and we try to predict the age value. Okay, so we are going to actually look at these connectivity matrices here. So here, what we can see is the number of subjects we have, so around 150, and the number of features. So the number of features you can see is massive. Why? Because the connectivity matrix is a matrix which is around 64 by 64, and each entry of this matrix will be used as a feature. That's why we have so many features. But one question I wanted to ask you, when you look at this data, do you notice something? So I just looked at this data 2 days ago, so it's really new for me as well. Actually, the first thing I notice is here, this region, which looks kind of dirty. And immediately, because it's so important to look at the data, I just plot it slightly differently. So just without interpolation, you can see indeed it looks quite dirty. And when you look closely, it seems that in between row 36 and 63, you have these dirty rows. So then I decided to have a bit look into it for this in the phenotype. What are these subjects in corresponding to these indices? And what I saw is that all the age group is for the very young kids. And it's not a surprise because, as you know, the very young kids, it's very hard to have them still in the scanner, and motion can really affect the signal. So it's just a demonstration why it's so important to always look at your data to understand what's going on. So I'm not going to remove this data yet. I will do an example with, but it will be very interesting to see what will be the results without this data. So here I decided to do just a quick investigation of the standard deviation of these features according to the subjects. And we can see here between subject number 36 to subject number 63, all these high standard deviation of the features correspond to all the subjects having an age less than 5. So in red is all the subjects with age less than 5, which I overlaid on the plot of the standard deviation of the features. And you can see that indeed there seems to be an issue with children less than 5. So as I say, I just got this data 2 days ago. I just looked at it 2 days ago, and I didn't have much time to do much than that, but it's just to show you that the quality analysis of your data is super important. Okay, so now just looking at the number of subjects per age group, we can see that actually we have young kids until 12 and then adults. So we have this gap of age. Actually, we can plot the histogram, the distribution of age. Here's at the age, and here is the number. You have all these kids and the adults. So the idea is to predict age doing a regression task. But I'm not comfortable with doing a regression task with this gap, because what can happen is that you can have two clusters and just try to fit a line. And it will not be really a regression, but it will be driven by these two clusters, leveraging the regression coefficients. So instead, we are going to remove the adults and just try to do the regression within this group. So if we cut the age at 13, we can see we still have 122 subjects. So we'll do that. Okay. So here I take all the subjects less than 15. So our Y to predict will be the age. And we select only where people are less than 13. So it's a Boolean mask here. And we chose only the one less than 13. And we do the same mask to select our features. So we take all the features, like 2,000 of them, but we select only the subjects who are less than 13. Okay. So number of features is 2016, and number of subjects is 122. So with that number of features, you can really expect some serious overfitting. So we'll just split our dataset to have round numbers, let's say 100 in train and 22 in test, and we'll shuffle. And I think it's very important because this data actually is ordered somehow by age, I think. And what's important also is to do stratification. So stratification is when you create the folds to have the same proportion of the class you want to predict in each fold. So it's typically used for classification, almost never, I mean, very rarely for regression. But in this case, in the data frame we looked at, there was this age group categories. So we'll use it to do this stratification to have in the traced, train, and test sets the same proportion of age groups. Okay, so we already know the train test split, but here you can indicate as many arrays as you want. So instead of the X and Y here, I will use the age class. And here just the indices going from 0 to the number of subjects to see how they are split. What's very important here is the stratify argument, age class. So it will have the same proportion of different age categories in train and test. And we ask here to have 122 subjects in the test size. So here you can either give a fraction like last time, like 0.4, or you can give an absolute number. It will automatically understand because the fraction is always less than 1. Okay. And here we just check that the stratification worked. And indeed, if we plot this distribution of age in train and test, it's the same. So we'll just look at the classic linear model. So we should have less performance in testing, obviously. So we just do things as before. Oops. So manually, remember, we just iterate over the fold. So we do a stratified K fold with a 10 fold, while stratified because it's stratified by age again. So we did this stratification for train and test. We put the test, we will never use it until the very end, and we do everything within the train. So the stratified K fold will be in the train. So as I showed in the presentation, in the training set, we split it into 10 folds. And in each fold, we are going to predict to have the performance on a train set and also on the test fold. And we save the results for R2 and mean square error. So we have train test for R2 and train test for square error. Okay. Yes, that it was. You don't have to worry about that. I had to create a new class to which is derived from the stratified k-fold, because normally you cannot use stratification in a regression because it's always based on your label y. So if your label y do not contain categories, you cannot do it. So I had to create a new class. So you don't have to worry about that. And here we use cross-validate because instead of iterating, it's so much easier to use the utility function sklearn provide. So we use cross-validate with our linear model on X-train and Y-train. We have a special cross-validation object. On the scoring function, we want R2 on negative mean square. Why negative? Again, so that higher is better. It's just a convenience thing. Okay, that's quite fast. We can already plot the results. And again, you can see here how limited is the R-squared in the testing set. And same for mean square error. You cannot even see it on training because in training, with that many features, you have a perfect fit. You can see the R2 is 1 and mean square 0 is 0, but it's so close to 0, it's not even plotted. Here, if you look at the box plot, indeed, you have 1 in R2, 0 in mean square error. But obviously, it's a perfect illustration of overfitting. When you try in the testing, the performance is much worse. So now we are going to add a feature selection process. And the thing we are going to do is we are going to look at two different types of feature selection, either with F-score or a mutual info scores. So what does it do is it's going to look at the correlation with your feature on the target, in this case age, and it's going only to keep the n best. So what is n? So what is here the k best? So what is k? It's for you to choose. So you call this select k best object with, you have to choose yourself what is the criteria. So we're going to select the k best going to F score, and here according to mutual info score. So you need to create a pipeline. I mean, we'll do it for convenience. First calling this feature selection. So it's going only to keep the 10 best, and then it's going to do linear regression with this k best. Again, this pipeline is super useful in this case. So here we call the special stratified k-fold. You don't have to do it. You can just call a normal k-fold. It's fine as well. But what's very important is to shuffle because the data is ordered. So it's a critical step. We create a dictionary to keep our scores in each fold for each model. And so for each model in a loop, we just have two models. We will call cross-validate with a list of scoring and save the results. Okay, and now we can. This one, I just rename the model, otherwise in the plots it's terrible, and create a data frame, and then we can plot it. Here as a plot. So in this case, you can see in the training is no longer perfect score because we only have 10 features, but in the testing, it's not that great. It's not much better. So we're going to look at another approach, but at least you saw how you can do feature selection. We're looking at the range of a hyperparameter. A hyperparameter, it means a parameter which is not part of your model. It's not the model parameters. It's a parameter which is above that. It's not within your model. It's just to even influence the model itself. So what's very convenient again is the validation curve. The validation curve is going to try many different parameters, for example, hyperparameters, many different k in this case. K is not a parameter of your model, is to change the way the model is going to behave. And we are going to plot the score for each value of this k. So it's going to do a loop for all this k range. And the validation curve methods is going to do cross-validation. So in this case, you can give which score you want. We're going to do with R2, so with the mean square error. And for each of these k value is going to do cross-validation, and we'll be able to compare the different performance. So it may take just a bit of time, and we save the results. I created a dedicated function to transform the output of validation curve to a data frame, which is much easier to plot. So this one is a function I wrote myself. You can see in the notebook. Yes, you can see I'm doing everything twice. Once for R2, once for mean square error, using either the pipeline with the F score as feature selection or the mutual information as feature selection. Something important. If you have just a single model, the parameter name will just be K, for example. If I just wanted to do this validation curve directly with the feature selection, I will use K. But because if it's a pipeline, because it is a pipeline, you need to put the name of your model, 2 underscore, and the name of the parameter. I'm going to plot this. I need to show the code. I'm not going to show any of the code for plotting because it's not really useful. So here you can see for the parameter k what is the value of the score for R2 and mean square error, and you can see that as you tend to have many parameters, you will overfit, so that's the training in blue, but the testing performance will be very poor. And you can see that actually the best performance in this case is for up to 25 parameters. But even this best performance is not that great. It's around 0.25 for R squared. So it's not, I mean, this model in this situation doesn't work well, but at least you can really see how to do it when you need to do cross-validation of an hyperparameter. So in this case, we are going to look at the relationship between the predicted and real value with cross-val predicts. I'm not sure if I'm missing something. Let me see. Oh no, it's fine. Okay. Yes, no, there is something missing. Sorry, I will just run this cell up. So here in this cell, we do the same as before, but we use the convenient function cross-val predict, which does everything in one go. And then we're going to plot it. So now I can put back the presentation. Here we are. So what we did here, we use cross-val predict, which is going to take the prediction in each test fall only and keep them. So you do your k-fall, you just have one test fall, so it saves the prediction. You have the prediction on the second test fall, is going to concatenate them for each of your fold. So that's a pretty useful function, because now we have our prediction from each of the test falls, or unseen data, concatenated, and we can plot our prediction as a function of the true age. And here you can see the R squared of 0.30. Okay. And what we can see, there seems to be a power law. So we could take the log of the age to have a more linear fit. I will do that quickly. That's not the most interesting part, but just for you to know you can do it. So there is a special object called transform target regressor, and you just have to call it with your estimator here. So we use a pipeline as estimator, and we just use it in our cross-val predict framework. So if we use it instead, you can see indeed it's more linear when you have a slightly higher R squared. Okay, so now the most interesting part is the penalized regression. So we use lasso in this case. So we just have to call the model. Again, it's an object, and we use a random state, which will condition the way a lasso is, the parameters are computed. And in this case, we will want to look at all kind of these lambda parameters, the penalized parameter, you remember from the slides. In this case, it's called alpha in sklearn. So we want to find the best penalizing parameter, which gives us the best testing fold prediction. So we look at all this range, and so many different alpha. Yeah, so in this case, it may take some time to run, but what we'll be able to do with this validation curve again is to look at the performance as alpha is changed. And remember, the bigger alpha is, the bigger penalty, the fewer number of parameters we have in our model. Okay. And that's it. So here you can see the different value of alpha. You can see that with a low value, which means low penalty, we have many parameters. We are overfitting with a very high performance trades in training, but low performance in testing. And we can see that the best parameters you are always interested in the testing performance. Here, the training performance is just to know if you're overfitting or not. And it seems to be around here, so around 0.05. So actually, we'll take as a choice 0.05. It will be our best model, let's say, and we'll use cross-validation to know how is this model doing. And in this case, you can see that it's pretty good, it's 0.46. But as we mentioned earlier, it's not so good to do cross-validation to compare different hyperparameters. What is best is to do nested cross-validation. And so we can implement that. We have a special, again, utility object, lasso CV, which will do cross-validation for us. So we can just call this lasso cross-validation object. And when we are going to do this scaffold, this cross-validation with a K fold, inside the fold, we are going to call the cross-validation of lasso. If you remember the slides, within each fold, we are going to do cross-validation inside, so that for each K iteration, we are going to have an estimation of the best alpha parameters. And what will be very interesting to see if the alpha is the same for each of the K split, or if it's different, and also what is the performance all the time. So instead of talking, I should have run it. Let's go back. And I will be able to plot the results. So here again, it's just for plotting. Here we are. So we see for each of the 10-fold, we can have an estimation of the R2 on mean square error. And in this case, you can see that the lasso model is doing relatively well. But every time it's for the best alpha. So let's check if the alpha is stable. And we can see it's relatively stable, but not completely. But we are going to take, so it's important now to remember that the higher alpha, the fewer parameters in a model, because there is more penalty. So we'll take one of them, for example, this one, which is close to the median, as our final model. So to analyze the final model, we'll finally be able to test it on the testing set we put aside. So that's the only time when you can fit on your whole training datasets to have your final evaluation on the test set you kept aside the whole time. So our final choice is this one. We fit our whole training data, and then we test it on this test set we kept from the beginning, using still R2 on mean square error as a performance estimate. And actually, we have a pretty good, a reasonably good R squared with the model. So you could see the whole pipeline on how to fit, as to select the best model with cross-validation, nested cross-validation with hyperparameter tuning. Hyperparameter tuning is a choice of the best hyperparameter. So that was a quite dense, but at least you could see the whole workflow. Now, what's very important in your imaging is to be able to interpret a model. It's not always the case. It's not always easy in machine learning, but for lasso, you can look at the coefficients. So remember, we can access the attributes of our object just with a coef. So in this case, we have 2016 coefficients. Means that the length, but many will be 0 thanks to this penalty term. And actually, we can see we have, if we count the number of non-zero, we have 33 parameters remaining out of the 2000. So it really be extremely helpful to be able to interpret more easily your model. So since each parameter is associated to a brain connection, we can do a brain plot, and that's the NiLearn part. So I'm just going to check how we are doing on time. Okay, so unfortunately we are doing very badly on time. It's my fault. So we have I used all the time. So I'm just going to summarize very quickly, finishing off the section. So if you go up to section 3, what I wanted to say about NiLearn, actually it was just to show an example on how to use it on fMRI data, but it's really specialized to fMRI, on how the vocabulary, the terminology used by NiLearn is the same as sklearn. So you still have this object you call every time you want to do something. So here is to measure connectivity. You have this fit transform method to apply. So again, there are lots of great tutorials on NiLearn, so you can really reuse it easily, and you can go through the Jupyter Notebook. There is everything in it. And just to, yes, that was the last. This section on NiLearn was on how to process fMRI data. It was how to turn your fMRI data into the shape sklearn is expecting. So the shape is the one we presented at the beginning of the presentation, which is an X matrix with all your observations as rows and all your features as columns. And the main exercise was to transform the connectivity matrix, which is 64 by 64, into a vector, because this vector will be all your features. And for each subject, you have to concatenate these features to build your feature matrix. And your Y label was just the age, so there was no difficulty in this case. So I'm going to conclude going back to the presentation. And I had a brief section on classification. But for classification, what changed is your labels, which are categories. They are no longer continuous, but they are categories. And the scores in this case is the number of good categorization, so true positive, true negative, and how bad you did when you, instead of predicting the patient did not have a disease, you had a false negative. And if you predicted he had the disease but he didn't, it's a false positive. And all the different scores are just a function of these ones. For example, you have the true positive rate, which is the number of true positive you detected compared to the total number of positive patients, and the false positive rate, which is number of false positive among all the negative. And so either you can use any of these metrics, but you have to know that most classification algorithms output a probability of having the disease or not. So, and you can choose what probability is a threshold to say yes, he has a disease, or no, he doesn't have it. You can choose p equals 0.5, p equals 0.95, depending on what is important to you. So I will just conclude for this classification part that what's very useful is to have this ROC curve to be able to look at every time you're going to choose a different probability, you're going to have a different false positive rate and true positive rate. And by going from 0 to 1 for this probability threshold, you'll be able to trace these curves. And the closer you are to the perfect classification, the better. So typically, you measure the area under the curve, AUC, to have a performance of your classifier. There was a section on SVM. I'm going to skip that. But what you can do is look at this slide and do the Nylon HAX-B dataset tutorial with use SVM for classification. And so here, so today we saw classification, regression, mostly regression, which are associated to label data. We have the dataset with both features and the label we want to predict. That's called supervised learning. But when you don't have an outcome, a label outcome, this is called unsupervised learning, which includes dimensionality reduction, which is mostly for visualization. When you have tons of features, you can actually project them only in 2 dimensions to try to understand your data. You can see there are different groups. And you also have clustering as unsupervised learning. In this case, you really try to understand if there are subgroups within your data. And it can be applied to the brain by, for example, grouping together vertices which look similar according to the MRI measures, and to have different regions. And it's often used actually to parcellate the brain clustering. But you don't have any label, so you just have your X feature matrix. So that's it. Thanks a lot for following along. It was quite dense, and I didn't even have time to finish, but hopefully it was quite useful for you to have an overview of machine learning and how to use it with sklearn. You have the same terminology in sklearn and Nylon, so if you understand the main idea, the main framework, you can really do it yourself, especially considering all the great examples and documentation in both sklearn and Nylon. It's really easy. It is made easy for the user to really try different approaches. So I would really encourage you to do so, even if you are working with EEG, with MNE, which have the same kind of tutorial. So that's it. I would just like shamelessly to also present the Brainhack we're going to have in autumn in Geneva. Hopefully it will not be remote, but everyone is invited, and you can check the website. We often have cool projects. You can also propose any project you want, as long as it's related to the brain. It can be EEG, MRI, or even 3D printing. And don't hesitate to follow us on Twitter to be aware of the next Brainhack. So thanks a lot. Ciao, ciao. And if you have any questions, yeah, absolutely not hesitate. I'm here in the chat. Thanks a lot.
Hi, everyone. So now we have some time set aside for a non-conference session, and Eduardo and I both linked the same document in the chat, but it's where if you still want to give a non-conference and you haven't signed up to do so, you can still sign up there, or I mean, ping us here as well since we're already in the session. So I'm hoping Dorota is here because she's the first person who signed up.
Yes.
I'm going to invite her on screen. And then, yeah, because not many people have signed up, we might just have time to have more of a proper break before the next session. Oh, Alejandro, you're going first? I invited Dorota. Okay. Oh, okay, Dorota asked me to. Cool. I will invite Alejandro then. Okay.
Hello. Hey.
Hello.
Hi.
Hi. How's it going?
Pretty
Doing
much.
well.
Is it look okay for everybody? My thing looks funny for some reason, but I think it's fine.
No, you look good.
Okay, good. So let me just jump right in. I'm pretty much just gonna do shameless self-promotion, but you know that's what the conference is for. And so let me just go ahead and share my screen. Let's see which window. This one here. All right, I am screen sharing. So basically what I want to talk about today is just something that I've been working on called NeuroScout. A lot of you have heard this before, but if you haven't, stick around because it's really fun and you can actually play with it yourself. NeuroScout is a cloud-based platform for the flexible reanalysis of naturalistic fMRI data. So basically, the idea is to take these publicly available data sets with complex naturalistic stimuli and make that really easy for you to reanalyze. So how do we do this? I'm just going to jump right in and go really quick. But basically, the idea is that NeuroScout is a web-based platform that draws from sources such as OpenFMRI and actually OpenNeuro now with BIDS data sets that are already pre-processed. And we basically just use algorithms from basically Google or other machine learning, deep learning algorithms to basically automatically annotate these data sets. So for example, it's really easy for Google to know that you took a picture of a cat because it has a deep learning model that can learn that's what cats look like. So we've developed a library called Pliers that takes advantage of a lot of existing algorithms and a lot of services that are out there to basically annotate these naturalistic data sets automatically. So I'm not going to play this video at the request of Greg because he said I played this video too many times, but essentially, essentially this will, as you can see in the still, you can automatically detect faces. You can annotate with tags the different things going on screen. You can annotate with the speech going on. We've extracted the speech, so you can actually annotate like the frequency of the words or the concreteness of the words that are being spoken. And you can, okay, Eduardo wants me to play it, so I'm just going to play it.
Sorry, Greg. Not sorry.
It's okay. I don't know if you can hear it, the video.
No.
We can't.
Don't worry about the sound. It's actually even better because then I can keep talking. But this is actually a stimuli from the HCP dataset. And so on the top right, you'll see the image tags from Clarify, which is a service for image analysis. And it's trying to detect what's going on screen. And in the red bounding boxes, you can see that it's detecting the faces and the location and the size of the faces. And on the bottom right, you can see a transcript and also a plot of the different norms that we've extracted on this transcript. So for example, the words that are happening right now are different frequency, different concreteness, different valence. So we can sort of automatically create timelines of predictors across the whole stimuli that reflect what's going on. So that's the clip. It's a good one, and I've played it for the last 4 years.
I think Chris Marcus also disapproved.
I know.
I mean,
okay.
I've seen this multiple times now.
It's a crowd favorite. People can't get enough of it. And so essentially it lets you to turn that into this, right? So this is a set of neural predictors that are going on across the whole movie. And we can do all sorts of things, like we can do audio features, we can do the tags, for example, whether a scene is outdoors or indoors, like that's the second row right there. And so we pairing up, yeah, Satra liked the video. And so we're pairing this up with really like a whole platform. So one part of it is the feature extraction, right? And the other part of it is that we need a whole machine readable process for analyzing neuroimaging data. So we have data, we have the feature extraction, but now we need a model specification. So I'm not going to go into detail here, but we've developed a model specification for describing GLMs. And so it's a JSON thing. It's called bid stats model. And this basically lets you specify everything you're doing to your design matrix, including scaling, including which variables, including the contrasts in a machine readable way. And actually Chris Markovich, who's complaining about the video in the chat, he has worked on FitLens, which is a NiPipe workflow for actually taking a BIDS data set and then taking the specification and actually producing results. So that's basically what NeurScout is. It's a web app, and it's a bunch of glue, and it's FitLens, and all of that together lets you basically go on the web and create a model, and then that model is given a unique ID, and you can just simply type NeurScout run and your unique ID. And then thanks to Data Lab, which you've already heard about today, thanks to OpenNeuro, thanks to NiPipe, thanks to all these amazing resources that this community has produced, NeurScout just basically glues all that stuff together and is able to fetch the data, is able to fetch the software dependencies, is able to provide a portable BIDS app that makes this all very, very, very easy. So you don't have to do anything except thinking about the science and thinking about the questions that you actually want to answer. And of course, at the very end, it will also allow you to share your findings by automatically uploading the results to NeuroVault. So it's trying to really shorten the gap between discovery and sharing results for these naturalistic data sets. And the idea is that this will help generate hypotheses that you can then go test in a study. So no one's saying don't run studies, but it's saying this is a great way to complement hypothesis generation. And so you can go from this stimuli to brain results. So that's pretty much the presentation. And I think that's the fastest I've ever given it. And yeah, I just want to say thank you to all these people. But I also just want to, since I'm actually live and I can share my screen, just show you NeurScout. So you can actually go right now, neurscout.org. So just do it. Go to neurscout.org and try it out yourself. So you basically just sign up for an account. And then I can just basically say, okay, I want to make a new analysis. So I can say, okay, this is my hackathon analysis, okay? And I can select one of the data sets that we've already ingested. So we have here about 9 data sets right now. And so I can, for example, select this Sherlock Merlin data set. I can select which of the tasks in the data set I want to analyze. And then I can search from all these predictors that have been extracted. So I could, for example, search that outdoor predictor that I showed you earlier and select it. I can also select something like the frequency of the speech that I mentioned earlier. Select one of these. There's a bunch of different ones. So I'll just go with this one for now. Let's see if that works. Actually, you know what? No, I'm not going to do that one because that requires doing something else. Let's just do speech. And I can also specify some transformations like scaling, things of that nature, which I'm not going to do right now. I can select which ones of the variables I'm going to convolve. In this case, all of them. You could also select predictors from fMRI prep, which are already extracted, which you wouldn't want to convolve, for example. I'm just going to generate a contrast for each one of these. And then this will pull up a design matrix. So right now it's going and creating that design matrix. So I'm just going to cheat like a cooking show and show you one that I've already made. And so basically, you can actually look at your design matrix. You can see the time course of the events. You can take a look at your correlation matrix and see how these variables relate to each other. And once you're happy enough with this, you can compile it, which will basically create all the files you need to run everything. And then with this one command, you should be able to run that analysis if you have Docker installed. So, oh, and of course, once you publish the results, we also make it easy to cite the appropriate papers and software and everything else. So go try it. It's pretty much ready. We've been kind of like the last couple of years like, oh, it's in beta, but now just go try it. If it breaks, let me know, and I'll be the one that probably has to go and fix it.
So Alejandro, there's a question from Yar. Asking,
yeah.
Are there he said, are there Git repos or datalog datasets with the already extracted and annotations for those datasets on NeuroScout?
Are there Git repos for that? No, there are not Git repos for that, but we do have an API. And so one thing I didn't talk about today is there's a, if you go to GitHub and search NeuroScout, you'll find PyNS or Pines, which nobody agrees that you should pronounce it that way. But that's basically the API library for our API. And so that will let you query the predictors. And so you can actually pull all of these predictors for any data set into like a pandas data frame and do whatever you want with it. So it's all open. We also have a repo with all the fMRI prep data sets that we process. So it's all sort of modular and open. So we just are designing it with the purpose of it being used through the web app. And so of course, like this audience, there's a lot of like, you know, I don't know, like power users, I guess. So they want to pull the data. But I think most people will hopefully just be happy with this. But if you're not, you can use the library to also create analyses and push them and look at the reports. So that's good for like people that are more comfortable with that and maybe want to do more advanced models.
I don't know if we should ask Chris's question. How do you think it's pronounced, or how do people think it's pronounced? You can ignore this question if you'd like to.
I will ignore this question. I'll let you guys figure that one out.
And there was a question from Yorick right before that. What was the end verdict with the negative FFA activation results?
Okay, so that one is really cool. And I shouldn't totally spoil this, but I will. Because we're hoping to wrap up a manuscript soon. So you'll see the results soon. But basically, one of the things that was really interesting, and one of the things I guess is really exciting about NeuroScout, is the ability to not just analyze one data set, right? But analyze multiple data sets. Because if you find something weird in one data set, especially naturalistic data set, you could say, well, maybe the data was just weird, you know? Like some of these tasks are not representative of everything that you could see. Some of them are quite contrived. And so what we were finding in the forest, which is what he's talking about, is that we really couldn't get FFA. And so when we found faces and we tagged them, we weren't getting FFA. So that's really weird, right? What's actually going on is that you do get FFA, but only really do you see a strong signal when it's the first time you've seen a specific face, or it's been a very long time since you saw that particular person. So we're used the clustering algorithm to identify these faces and then group them into clusters and then calculate the time in between presentations. And that's when you start seeing a stronger response. So that was a pretty cool finding that I don't think we would have believed otherwise. But the thing that made it really believable, and as you'll see in the preprint, is that we can actually do a meta-analysis across all of these data sets and then actually feel more confident that this is not just, you know, something that we saw in one data set. So you'll see more from that soon. And the other thing I want to plug too is if you want to hear more about this, or Pliers, which is the library to do the extraction yourself in case you want to just work outside of the workflow. There's a OHBM educational session. And so that's actually happening in July because I think it's going after the conference this year. And Luke Chang and Emily Finn and some other folks have put together a session on how to analyze naturalistic data. So that's going to be really cool because it's very experimental. Nobody really knows how to do it. And so I'll be talking about Pliers and NeurScout in more detail there if you want to follow up on that.
Awesome. We are running out of time and are still behind schedule, so I think we're going to move on
I
to
told you I
the
could talk a lot. You got to cut me off. Yeah, please.
Anyway, thank you for the presentation, Alejandro.
Yeah, thanks.
Cool. I will invite Dorota on stage now. And
afterwards we have Christine.
Okay. Do we? Because I thought that they were just gonna have to separate Zoom thing.
Oh, wait,
Sorry?
it says Zoom.
Can you hear me?
Sorry.
Yes.
Hi. You want me to go? Or-
Yes. Hi.
Is it fine?
Oh yeah.
Oh, yeah, sorry.
Yes,
We just had some miscommunication about another thing. Don't worry.
Okay. So, oh, okay. No, not this one. Okay, can you see my screen?
Not yet.
Oh, oh, okay, because I forgot to share it. Can you see it now? No.
Awesome. Just focus on
it. Okay. Thank you. Is it fine now?
Mm-hmm.
Okay. So my name is Dorota, and I just want to because I had presentation 2 days ago about our project, but we are working on development of Pydra, but we actually do not have. Didn't have time to explain what is Pydra and how it is part of NiPipe environment. So I just want to have a short introduction for this for people who never use Pydra or never used NiPipe. So basically, NiPipe 1 has been like 10 years and has been helping scientists to build scientific workflow and provides a uniform interfaces for many external software like FSL and FNI, Preserver, SBM. And it's actually behind the scene on many of your favorite tools like fMRI Prep or CPAC. So what we are trying to do now is just to build second generation of NiPipe that will provide more additional flexibility. And also we'll have various components in kind of more separated, not everything together as in NiPipe 1. So so one of the main library will be Pydra, that is a workflow engine. But we also want to combine this with NeuroDocker that some of you are using for create Docker files and security files. The Skaken that can be used as for regression testing and NiFlows to create workflows that can be tested and reused. So I'm sorry for this. I didn't create a completely new presentation. This is just a poster that I had to provide. I had to submit a month ago. So basically Pydra is a pretty lightweight data flow engine written in Python 3.7. As I mentioned before, it is meant to be general purpose, even though it's definitely designed by people who work on NiPipe. And one of the main concept behind Pydra is to provide tool that provides a very flexible MapReduce concept, and also helps you to reuse results from your workflows. So the main things that we think we are interested think that comparing to NiPipe, we provide more uniform API for task and workflow. Basically, we have multiple different tasks for function tasks, for shell command tasks, container tasks, etc. but also like every single workflow is a task. So that can help us to build like workflows that are like nested in any depth you want. One of the things is also like we want to provide support for many different workers. So it's either like concurrent features, Slurm, and task that is right now experimental. As I said, we work a lot on like kind of like mappers, map reduce idea. So we are providing like very flexible like splitter and combiner that like the next slide I will show more. And what is also like very important that we provide like global caching. So basically whenever you run a task and you provide a path to the output where you have your results, the new workflow can reuse the same results. And not only if it's like the same workflow, even if it's like this is like only like part of your new workflow, Python would be able to recognize that this specific task was run with this specific input and just use the cache results. So as I said before, we really like wanted to focus on like the MapReduce concept. So one of the nice things we provide is that the mapping and like or like splitting can be actually passed through an entire workflow. So not only we can work on like single task, but we actually wanna we can provide the same mapping that passes through the entire workflow. And this is like, yeah, so that was our presentation. And this is like, I just wanna like kind of provide this introduction, but this whole concept is actually in our tutorial. So I would just encourage you to go through the tutorial and ask a question. So one of the things that is like more maybe some people might be interested, like machine learning concept was like comparison of models from scikit-learn. This is the slide provided. This is mostly like done by Satya. He was working on this like model comparison, and this is you can find in PyDraw.ml repository as a kind of example of the application for PyDraw. So yeah, so at the end, like I just want to mention that we were hacking for like last 3 days, but we will be also like doing OHBM. So you can find us still on the channel. It will be like either NiPipe or HBM hack NiPipe because it's basically it was renamed for this hackathon. And also I just wanna like once again like kind of provide links to tutorial and the conference papers so you can ask questions during the next 2 weeks, and we can work together also like on create your own PyDraw workflow. Thank you
so much, Dorota.
Because I cannot see you when I'm presenting.
Oh, sorry. 1 second.
I don't know, it's like when you have full mode.
I will close your screen share. 1 sec. Cool. So we have one question about your presentation from Tashrif, which is, can you explain in simple terms what MapReduce is?
Yeah, so MapReduce, MapReduce, like original concept was like created by Google. So basically it's like if you have like the same task, the same function, but you want to run on like multiple inputs. So you basically like run the same function for every single input separately. And reduce is basically like maybe at the end you want to like kind of collect all of these outputs together. So this is like the basic concept of MapReduce. What is different in PyDraw that we can have this concept like that goes through multiple tasks in the workflow. So for example, you can map your input at the very beginning, run like multiple tasks, and reduce, kind of combine this output at the end of the workflow. Also, like in MapReduce, an original like version of MapReduce, you are doing this over like one input. In PyDraw, we want to have like a more flexible MapReduce concept. So we actually provide you can have any number of input you want, and you can also like kind of adding this mapping through the workflow and reducing this mapping. So it's kind of, and I like it's kind of hard to explain in like during like 2 minutes, but I think like there are some nice figures in tutorials, so you can see the concept.
Good to know. Thank you. And then Tashrif also had one more question, which is NicePipe definition of a node around a function required all imports and variables to be local to that function. Has Pydra improved upon that?
Oh, so it's the picking. So we wanna like I think like the main issue was like that it's like everything has to be like important in the task in the function, if I'm guessing correct the question, and we try to avoid this issue in Pydra, but we do have also one issue with.
Okay, thank you. So nobody else has signed up to give an unconference, so you can let us know now. Otherwise, we can either move on straight to the Brainart SIG presentations, or we can take a bit more of a break. I don't know what people want to do. If we want to actually stick to the schedule and start the wrap-up in an hour and 6 minutes, we would have to start the Brainart SIG presentations now. And after the wrap-up, which I think will end up taking longer than we had scheduled for just due to the number of projects that we have, there's also a social at 6 p.m. EST.
Okay, so there's one vote for break.
I mean, you can still take a break while the presentation is being shown. That is also an option.
Start with visualization and then Brainart, I think. Yes.
Sorry?
Well, it's both, actually. Sorry, she's asking about what's next. It's the same, right?
Oh, yeah, the visualization session is taught by the Brainart SIG.
Yes.
Yeah, it seems like most people aren't just starting the session. Yeah, okay. Yeah, Alejandro seconded what I was thinking as well, that yes, we have like 22 projects in this hub, so nobody seems to want to stick to about 3 to 5 minutes of presenting their work, which is completely understandable. But yeah, I guess we'll just move on then to the next session. And yeah, people can take a break if they want to. Cool, so thank you for coming to the unconferences, and thank you to Dorot and Alejandro for presenting their work. We will move everybody over to the next session.
Hello, everyone. My name is Chloe Telesford. I'm a research scientist at the Nathan Klein Institute in Orangeburg, New York. I would like to thank the organizers of the Brain Hackathon for inviting me to speak. Today, I will be presenting Visualizing Networks in Gephi. Now, there are a variety of software packages that visualize networks. The reason why I like Gephi is that it's relatively easy to use and because it allows you to visualize large-scale networks. If you've ever used a package like Pyac or NodeXL, you'll quickly recognize their limitations in large-scale networks. Gephi is not without bugs, of course, but I found it quite useful for visualizing systems. Now, Gephi is a network visualization program that you may use in your presentations, posters, or papers. As you may already know, a network is a system containing two elements, nodes and edges. The nodes represent things or objects in the system. In the case of neuroimaging data, that would be likely voxels or brain regions. Then you have your edges, which represents relationships between your nodes. And for neuroimaging data, that could be correlation values or streamlines between two different regions. Now, Gephi allows us to take such data and either import it or create networks within the software package. It also allows you to analyze these networks using various graph metrics like clustering coefficient, path length, degree centrality, and a variety of other measures. The software most importantly contains various layout algorithms, which allows us to visualize the system, and that allows us to see the structure of the system. In this presentation, I'm going to show you how to import data, calculate a few basic graph metrics, and then visualize the network based on those metrics. You can find Gephi at gephi.org. It is available for Windows, Mac, and Linux. It's relatively straightforward. Download the software and install it. You'll also have to make sure that you have the most recent version of Java, as this is what it uses in its software package. Before we get started though, I want to show you some configuration tricks you'll probably need to get the most out of the software. So once you go to gephi.org, download it, install it, and then once you've installed it, you go to your Gephi etc folder in the Gephi installation, and you're going to see a file called gephi.conf, which is our configuration file. One of the problems you may run into is that the software may not load at all, or you can load the software, import a network, and then it will crash in the middle of doing anything. And this really comes down to issues within your configuration file. So you're going to want to focus on two different lines. One is the one under default options. Here it is line 7. And for this, you'll see that I have a range of 64 megabytes to 240 megabytes. I'm not sure what the default is. It's either 512 megabytes or 1024 megabytes. Regardless, the main issue is that if your memory heap size is too small, then the software will crash because it will run out of memory. And of course, this is also based on the amount of RAM that you have in your system. The next line is the JDK home. Here is line 13. And this is where you tell Gephi where your Java installation is. Now, it may not be a problem for other people, but one of the problems that I had was that because I have a 64-bit version of Windows, when I install Java, it installs a 32-bit and a 64-bit version. And if Gephi tries to go to the 32-bit version by default, it will have problems running the software. So I have to explicitly tell it, use the 64-bit version to use it properly. Of course, when you do it this way, whenever you update Java, then you'll have to update this configuration file so it is pointed to the proper Java installation. But you may not have this issue, but if you do have these issues, these are two of the main areas that you might have to play around with to get Gephi to run on your machine. And just to give you a sense of what you can do with Gephi, here is the Marvel Cinematic Universe. You may have seen this 2 years ago on the subreddit Data is Beautiful. And this is something I updated last year. And what you're looking at are all the nodes are representing characters in the system or the movies. And the size of the node tells you how much screen time a character had. And the lines or edges between the nodes tell you how much screen time these characters share with each other. You'll also notice that these nodes have different colors, and these colors represent the groupings or community structure between different nodes. And what that really shows is that characters that appear in the same movies will be grouped together. And that, of course, makes lots of sense. When you're looking at neuroimaging data, of course, you're going to be looking at either some sort of structural connections or functional connections, and you can see which nodes are grouped with each other based on function. For this tutorial, though, I will not be using any neuroimaging data or even the Marvel Cinematic Universe, because they are very large networks and they also will just run very slowly on my machine. So I've chosen another network based on the HBO series The Wire, and I have fewer nodes. So let's just hop right into Gephi. So whenever you open Gephi, I've already opened it, you're going to get a welcome screen, and that welcome screen will show you the recent networks that you've opened. It will also give you the option to create a new network, or you can look at some of the sample networks that come with the software by default. I've already chosen new project, and you're going to see I have this overview screen. But let's hop right over to the data laboratory. Now, the data laboratory is the space in which you will be importing all your data, whether it's information about your nodes or information about your edges. It will also be where I can see the metrics and the values associated with my nodes. And then I can also use various tools like exporting that information to a table, and then I can use that with whatever my analyses are. But before we actually start pulling in some information into the screen, I'm first going to show you my actual data. So I have that stored in Excel right now. And so I have two different tables here. One is my nodes table, and that contains a column for ID and label. Now in this particular network, I have 90 nodes, and each of those nodes has a label which represents a specific character. Now for the ID, mine is numeric, but it doesn't have to be numeric. It can also be text, but because my data started out in an adjacency matrix in MATLAB, I just used the row for my different nodes to represent my ID, and the label would actually have my actual text label. If you're dealing with neuroimaging data, of course, you could have each of your rows representing a node, and the label can represent a brain region. So you could have visual cortex or parietal lobe. It's just however you have your network organized. The next table I have are my edges. And my edges has several columns. I have source, target, weight, type, and ID. Now the ID in this case, this represents an ID for my edges. So it's not like the ID for my nodes. The ID for my nodes are what you'll find in source and target. So you want to make sure that whatever you use for your source and target, whatever those IDs are, they need to match whatever is in your node table. But let's just start backwards from these columns. If we look at ID, this goes from 0 to the number of edges I have. You can either have IDs based on groupings of the nodes. In this case, it doesn't matter, so it's all ordinal. The next column I have is type, and that will tell me whether my network is directed or undirected. Because this is a symmetric network and undirected, everything is undirected, of course. But let's say you have a directed network where you have histology data, then you may want to have a directed network, and then you'll have to change the type of edge that you have here. Next is weight. In this case, weight represents how much shared screen time two characters have. In neuroimaging data, that can be correlation between two different regions, or they could be the number of streamlines, like in, say, DTI data. And of course, finally, we have our source and target, which is telling you what two nodes are connected to each other. In an undirected network, connecting 1 and 3 and 3 and 1 doesn't matter. But if for a directed network, it's actually critical that your source to your target is in the right direction. But now that we see the data and how it's stored, we can now import that into Gephi. Now, the data that I have here is stored as Excel files, but you can also import this data as CSV files, which is what I did when I used this software in Linux. So when I want to now pull my data into Gephi, I'll click on Import Spreadsheet right here. and then I will select my nodes table. And once I've done that, I will now have a bunch of data here. You'll see my ID, my labels. I have actor, and I also have this column called screen time. But the important thing you want to make sure of is that what you're importing your table as. I'm importing it as a nodes table. After that, I'll click next. And then I can say, what columns do I want to keep when I'm importing? In this case, I'm going to leave out the actors because I don't care about the actor column. So I'll deselect that. And then you'll see screen time. It will be imported as an integer. You can also import it as a double, but I'm going to leave it as an integer. And then I'll hit finish. Now, when I create my new workspace, you'll see I have something that says workspace 1. And when I'm importing this data, I can say, do I want to create a brand new workspace, or do I want to actually append it to my already open workspace? Now, since I already have workspace 1 already there, I'm going to say append to existing workspace. And now I have my nodes table in Gephi. Now I want to get my edges in. So I'm going to click import spreadsheet again. Then I'm going to select my edges and then hit open. You're going to see I have my source target weight like you saw on the Excel spreadsheet. It's critical that it says import as edges table. Then I'll hit next. And in this case, I'll keep all of my columns. And you'll notice that the weight, it is under the format double. Now, I could select integer, but I'll leave it as double. But if you're looking at something like neuroimaging data, you're going to want to make sure that it is a continuous value. So you'll keep double instead of saying integer. Then I'll hit finish. And I'll append to my existing table, my existing workspace, click OK. And now I have my nodes, and I click on my edges, I have my edges. So now we have all our data in Gephi. So now let's go to our overview screen to see what that network looks like. So when it imports all your nodes, they're going to be randomly connected to each other, and they're going to be randomly, or not randomly connected, but randomly organized on the screen. So we may want to get some information out of this network. So on the right side, you're going to see we have 90 nodes, 458 edges. It's an undirected graph. But now we can start to calculate some statistics. Now there are a variety of statistics that I can choose, but I'm just going to look at degree. And click on degree here. And you're going to see that it's going to calculate the number of edges for each node and also give you a distribution. And when you can save that, but in this case, I'll just click close. And the other metric I want to look at is community structure. So I'll click on modularity and have it run the modularity. So I'll keep the defaults, hit OK, and then it will tell me how many communities it finds and the number of nodes it finds in each community. Now, with community structure, but this particular algorithm is not deterministic. So if I run this again, I'll get a different result. So if I run again, I get a different result, 6 communities, run it again, different result, 6 communities, I got the same thing, run it again. And you can get different numbers of communities based on the number of times you've run it. So I'm just going to leave it at this one that says I have 7 communities. And I'm just going to now close these all out. And now that is stored in my system. So if I go back to my data laboratory, you'll now notice that when I click on the nodes, I now have these 2 new columns. I have one for degree, so I can see which nodes have the most connections. And I also have one for modularity class, so I can see what communities do nodes fall in. But back to my overview, again, we've seen no changes to my nodes on the screen. We see these very thick edges, but the nodes are all over the place. So one thing that we can do is start to looking at ways to change the appearance of the nodes. So if we go to the left side here, we have appearance. And we have this little palette here, so that means that we can change the colors. So one of the best ways to look at the nodes is to look at how they're partitioned. And that will group the nodes based on a certain color. So here, modularity class is perfect because we can now look at those communities that we have and then just say apply. And now we have these different colors representing the different nodes that group with each other more than the rest of the network. But this background is a little light, so we really can't see these nodes. So I can click this button over here and change the background. And now it's a little easier to see. However, how do we see what nodes are important? Well, we can change the size of the nodes. and click this over here. And we can change the ranking. Now we could choose something like degree and say if a node has more connections, it should be bigger. And I can hit apply here, and that will change the nodes based on nodes that have the most connections. In my case, you'll notice that I had a column called screen time. I think of the most important nodes, at least in this particular system, as the nodes that have the most screen time. So I'll click my screen time attribute, hit apply, and then it will change the size of the nodes based on how much screen time they actually had. You notice that I have a minimum size of 10, maximum size of 100, and this is a linear change. However, I can also click on this feature called spline and then change whatever my spline is for how these nodes grow in size. So if I use this one, I can see that the nodes now have a curved spline, but I'll stick with linear here. But of course, it still looks unorganized. You can see that some nodes are overlapping each other. And so you may want to get a sense of how does this network actually organize itself. So I will now choose a layout. And there are various layouts you choose. My favorite actually is Force Atlas 2. So if I just hit run, you'll see that the nodes kind of clump together. So to prevent that, I can click on Prevent Overlap. When I click Prevent Overlap, you'll see that these nodes now are ungrouped, are now grouped together, but it's now flying around. So I can now change my gravity and increase that. So I'm going to increase that to 100. That makes it come back to the center. And then I have my scaling. So that tells you how much these nodes repulse each other. So I'm going to choose 250. And now these nodes tend to push each other apart. And now this network is kind of organized based on how the nodes are connected to each other and how much screen time they have. So let's hit stop here. And then we can go right to preview to get a sense of how this is visualized. Now, if I were to just hit this refresh, I get this visualization of the network. But of course, I can play with the different parameters. So for instance, you can see all these edges are curved. I can go to edges and deselect that and say I want straight edges. And let's just say I want to have labels here. And so I can select my labels and hit refresh. You'll notice that these labels are now underneath my nodes. So I have to go to my renderer here, click Manage Renderers, and I'll go to my default node labels, and I will move them up so that when I hit refresh again, now they're on top of the edges. And then I can just zoom in and I can see the edges between different nodes. And we can see that the characters are representing in each of these circles. And of course, let's just say I don't like having a white background, so I'll just choose a grayscale background right here. And then if I hit that, then I actually can see the nodes more easily now. Reset my zoom, and now I can visualize my network here. And finally, I can just export this, and I can export it as a PDF, PNG, or a vector file. And in doing so, then I can now visualize my system and put that onto a poster or onto a paper, and then have a very nice visualization of my network. So with that, that is just the basic overview of using Gephi. If you have any questions, please feel free to ask. And I hope this will be helpful to you in any of the posters or presentations that you use in the future. And with that, I'd like to thank you and the organizers for inviting me.
Hello, everyone. I'm Leonardo Accarino, a postdoc at UCSF. Today, I'm very excited to give this short talk on brain visualization. And actually, very quick disclaimer to begin with, I'm not a professional programmer or graphic design expert. I'm really just a random postdoc working with neuroimaging data and perhaps with a particular interest in visualization. As a quick outline, I'm just going to share with you some general thoughts and maybe possible tips in the very first part of the presentation, like 6 or 7 slides, and then I'll go through an actual working example. So I will introduce some analysis I've run for a paper that was recently accepted, and then share with you the actual process, get into the final figures. As for the general thoughts, I think we can all agree that visualizing neuroimaging data on brains is all about pros and cons. And really, I could come up with these as like possible groupings, like general groupings of approaches to show neuroimaging data. And they range from the single or multi-slice, which I believe is very frequently adopted all around the literature, to the 3D, three-dimensional and surface rendering approaches, also very, very frequent, and then the flat maps. And I think you can kind of see along this fictional x-axis a different degree of complexity, right? All these approaches, I do believe, have pros and cons. And just running quickly through them, if we think of the single and multi-slice approach, I think it is, like the main pro is that it's really simple. It's easy to tweak. It's flexible because it's easy to design. You can choose the slices or the views or the planes and so on. It's safe because it's reproducible. If you're actually publishing your coordinates where you actually grab the slices, especially if you're in standard space, I think it's fairly easy to reproduce. And also it's accessible. There are so many software available. As main drawbacks to this approach that I could think of, I think one, of course, is that this approach by definition is partial because you're only showing some of the data, like not the full brain, but only some slices. And I think this also takes us to the next drawback, which is that this approach is prone to cherry picking. Like users may choose slices ad hoc to make their point, which, can kind of, I guess it's also about transparency, but it's an approach that, of course, being partial kind of wants you to pick slices to make your point. As for the three-dimensional and surface renderings, I do believe they are super informative. They convey a lot of info, and they're really easy in terms that I think they also they help in understanding the anatomy and the localization of the results. And also they are very immediate, like the data is visualized literally in a glance. However, they are more complex because they require methodological choices. For instance, the mapping algorithms or also the lighting algorithms of the figures. And they could be misleading because some of these choices could actually change the final visual result of the figure. As for the flat maps, I think they are very accurate because each voxel is represented, and also they're very precise because the shape of the structures is preserved. However, they're difficult because they require expertise, I think, of the reader to be fully understood and interpreted. And also they're not that available. There are not really like many softwares actually able to generate them easily, at least. And, as always, your choice will make the whole difference in the final outcome. As a sample example that I was thinking of, I literally just generated this functional connectivity map from NeuroSynth. And this is just a functional connectivity map originating from this seed, like from this voxel I clicked in the posterior cingulate. And literally, like NeuroSynth is using this multi-slice view as a default for the positive values. So you can see 3 planes, like a single slice for the axial, the coronal, and the sagittal. And of course, this is already giving you a lot of information. What I did was just downloading this NII, so nifty image, and plot it with Brainnet. So Brainnet is one of the possible software you can use running on MATLAB to do surface renderings. And this is exactly the same image. However, we do the Viridis color scale. And this is also an image showing only the positive values, just like the one you're seeing on the left, but it's a different visualization. And of course, gives you a bit more info compared to the multi-slice approach. One point that I wanted to make is that all these other figures that now I'm showing, they are all coming from exactly the same nifty image, but they do look a bit different, right? They along like this y-axis going from the top to the bottom, you can see that the topography and the intensity of the signal seems to change, of the result seems to change, but actually it's exactly the same image with the same range of values. So what I'm changing here is only the mapping algorithm, which is different across the 3 figures. And I believe this is really important because some of these regions or clusters look quite similar, so that doesn't make a lot of difference. But other clusters, like these ones, they literally like their appearance or their presence in the figure is totally related and dependent on the mapping algorithm you pick. And the question, I guess, is what is the right one? And the problem is that there is not really a gold standard or a unique solution. And it's kind of up to your responsibility to provide an accurate depiction of your results. For instance, you could also try different types of visualization and kind of understand whether this cluster is really there or not, and choose accordingly the visualization. And, you know, like, we are still talking about neuroimaging data, but you do not only show neuroimaging data with brains. You can also show neuroimaging data without brains, so with other types of visualization. And I just wanted to give a brief overview of some other approaches we have done in the past. And one is this paper by Renaud Lajoie, who is a colleague, another postdoc in my group. And here what you're looking at, I'm not going to go through the whole paper, of course, for the sake of time, but what you can see here is that basically he was testing the correlation between brain images, between pairs of brain images. And, you know, you could, for instance, here on this plot, I believe you can see, sorry, I'm going to just move this a bit upwards. I believe you can actually see here on the left that he was testing the correlation, for instance, between these two images here and also between these two images here. And, you know, qualitatively, you can kind of look at these images and understand that this one is looking way more like this in terms of gradients of the signal, and this one kind of looking less alike to this one. And this is, you know, a qualitative assessment. But going to these voxel-wise scatter plots he used, of course, was bringing the point home, I think, in a way more immediate way compared to just using brains. So switching to non-brain visualization for brain data actually worked pretty well. And, you know, like an alternative to this visualization is also using hexed scatter plots instead, which are a good alternative, and they also can provide a lot of data also on the density of the different voxels in the different ranges of values. This is another example from a previous paper of mine. And here what I was showing was just the extent of the different functional networks, like in terms of how big the networks were, like literally the number of voxels. And, you know, we had a lot of course, like brains and brain renderings for these results, but there were many. And what we were doing here is just comparing the size of these different networks across 3 different groups. So healthy controls, and then within 2 groups of patients with dementia with Lewy bodies, with or without hallucinations. And what we did at the end was using this radar plot that you can see here, because basically I think this really brought the point home that first, the healthy control networks were larger than the ones measured in the patients, and then also within the 2 subgroups of patients, you could kind of easily understand which ones were larger or smaller than the other, respectively. And then the third example I wanted to make is regarding this approach, which is, you know, a correlation matrix. This is a fairly common approach to show connectivity data, correlation data within brains. And you can see here, this is from an actual other paper of mine. And I'm actually also showing here the brain renderings, like the nodes and edges with visualization, to give you an idea. Like, I'm providing here exactly the same type of the same information, but probably the correlation matrix is easier to understand and to kind of grasp what regions are correlated with what compared to a crowded nodes and edges visualization. So this was just to give you an overview of how I believe non-brain visualization can be useful with brain data. Every time I'm making a figure, I have to say I feel like I'm making executive decisions to put myself somewhere here. So while I was preparing this talk, I came up with this, and I think it's pretty good. It's showing like you have to kind of put yourself somewhere across these different quadrants, right? Between simplicity and complexity and partiality and completeness of the info. And I was trying to think of my journey so far in my academic career, and this is an actual animation with myself going around in different quadrants, and I believe so far I'm kind of moving in the right direction to what I called the holy grail of visualization, which is an image that is very simple and it's complete. And I think on the way there is few things we can consider to make our figures, and these are of course always very humble opinions coming from me. The first, of course, is that as always, less is more. You always hear about less is more when you are attending a talk on visualization, and really crowded figures do cloud the interpretation. They make it harder to understand the results. The second thing that I want to say is that color scales, they are dramatically important. Changing color scale can totally alter the way you are conveying your findings. Of course, as I was mentioning before, I think it is really useful to combine brain and non-brain based visualization for neuroimaging data. I think can make things way more clear. And I think one important thing I wanted to stress is that complexity, at least to me, is not quality. When I see a complex figure, I'm always, it's not like I'm taking for granted that behind that there is a very high value, top-notch story. A figure, in my opinion, should always be self-explanatory. So a very complex figure may be not self-explanatory, which probably sometimes is not good. Another thing I wanted to say is that a good practice is always to clearly describe the methods you use to obtain the figure. For instance, especially if you're using renderings, which software you use and which parameters you use to actually create the rendering. And finally, of course, providing the actual images plotted, like the brain images, for instance, a T-map can help. And of course, there is public repositories right now, for instance, NeuroVault, to do it. And in that case, you're just providing the brain image, so you're kind of also providing the raw data used to make the figure. So let's switch to the working example. I'm not gonna describe in a lot of detail the paper, but this was a study on spatial extent. So basically, we studied how diffuse in the brain, so basically the percent of gray matter involved, were abnormalities measured with different modalities, including the amyloid PET, which is, if you're not familiar with, it's a neuroimaging technique that basically evaluates the amyloid plaques accumulation in the brain, and this is a signature of Alzheimer's disease. Tau PET, which is very similar to amyloid PET, but it's a different tracer, so it's actually targeting neurofibrillary tau tangles in the brain, which is another signature of Alzheimer's disease. And then finally, FDG PET, which is a neuroimaging technique investigating brain glucose metabolism. And basically, we had data for about 80 patients, and for all of them, we had these 3 scans. So just to give you an idea, this is a single case. This is an image of amyloid PET, which is PPET. The tracer is called PIP. And this is a tau PET image. The tracer is called FTP. And then finally, this is an FDG PET, and the tracer is FDG. What we did was comparing all these different images with a set of normal controls, and we ended up with these images that you can see here that are basically binary images, where each voxel with a 1, so appearing white here, is abnormal compared to the controls. So since we knew how big the mask was for the analysis, we could estimate what was the actual proportion. And here I'm just eyeballing them and say that, for instance, this image looks like it's 96% of the gray matter. The second one, this one, I believe, is around maybe 88, and then this one is way less, so about 4 or 5. So the story is, how do we convey this info? Like, how do we convey the spatial extent info for all these different subjects according to these 3 different modalities? Like giving this information using brains, even if this is brain data, would have been extremely difficult. So what we did was actually just go into box plots, which, it's a simple plot, but really takes the point in this case, because gives you first an immediate idea that the modality here in blue is way more extended compared to the green modality or the red modality, and also gives you the chance with individual points to understand that, for instance, in this modality, FTP, there were 2 different groups, one group here, like subgroups of patients, one group here, and one group here. So it's kind of an immediate approach. And then, of course, another question was, is it always that within each subject, this is the hierarchy, right? For instance, every given subject has more amyloid, and then some tau, and then some neurodegeneration. So they kind of go one step after the other. And also in this case, would have been very hard to show brains for all these patients. That would have been hundreds of brains. So instead, we're using spaghetti plots. And also in this case, I think these spaghetti plots really give you the idea and show you what are the possible hierarchies. You show the individual hierarchies in kind of gray on the background, and then we also identified the main hierarchies, which are the colored ones you are looking at now. So also these are 2 examples of non-brain visualization of neuroimaging data that we believe were very clear. So far, I'm actually completely missing a crucial info. If you were reading my paper, then I believe one question would be, what about the overlap? Like all these voxels could be positive or abnormal in these 3 different modalities, all of them, or like many different combinations of them, like 2 pairwise combinations. So what we did was basically, starting from these 3 binary images that I was telling you about, we summed them. So it's a very simple sum with the nearest neighbor interpolation. And you would end up with an image that looks like this, right? So it's a sum. And before the actual summing of the 3 binary images, we assigned unique values. And by doing so, we could identify then after the summing that we could, identify, yes, all the possible voxel classifications, like all the possible pairwise combination, and actually not pairwise, but all 3 of them, and how, like which one was positive and negative, and positive and negative across the whole brain. And this was done for each single subject. And this, of course, took us to the possibility of actually identifying groups of voxels that were defined according to the different 3-modality status. Once we had this, the question now was, how do we show these results, right? So there is 2 things about this story. One is where these voxels are across the group, and the other story is how many are these voxels across the patients. As for the first story, so where are those voxels? Of course, we kind of thought that the brain visualization would have been better and more informative, so we actually picked surface renderings, which is what you're looking at here. And you see, I think these really give an immediate message, that is that these different voxel classifications that you see on the bottom of the figures do have different localization across the brain. So these are frequency maps. So the story is kind of, voxels that belong to this classification tend to be here and here across the groups, while voxels that have this classification tend to be here and here, and so on. I think there is lots of info here, and it's really great to indicate what is the localization, but there is nothing about how many voxels belong to these groups to these classifications across our group. So to do so, we switch it again to non-brain data, and that's what you see here. This is like a Venn diagram, which maybe might not be the first thing you think about to show brain data, but in this case, I think it's really taking the point, because it's kind of, telling you what are the different intersections across the whole group between the different voxel categories. And if we know, the color, of course, and like the categories that you're seeing now on the right, we can estimate these numbers, which is the median number of voxels belonging to those different classifications for each single subject across the whole group. And also in this case, the Venn diagram is really helping us. So to wrap up, just to give you like few take-home messages, I believe that executive decisions on this visualization can really give you a completely different result with different trade-offs between partiality, reproducibility, quality, and also easiness of execution. So this also makes a lot of difference, I believe. And sometimes it's really difficult to find the balance between completeness and simplicity. And actually, this also depends on the audience and the target journal. So I believe also this is something that you should take into account. And then finally, that, and this is, I guess this is a kind of a personal take-home, effective neuroimaging data visualization does not necessarily require technical skills. I think it's more important to really think through all the possible visualization options and choose wisely to show all your data and be transparent about it. Of course, these are like very important things. Finally, I want to thank you for your attention. And of course, feel free to reach out to my email. You can see here my website and also on Twitter. And I wanted to actually thank also these amazing people that were involved in this session, Renaud Lajoie at UCSF and Valentina Borghesani at UMorel. And again, thank you for your attention. And I think I'm good with the timing.
So this talk, I'm going to tell you about how we use gradients to uncover the organization of the human brain, as well as how you can create gradients from your own data sets to use in your own research. But before I get into any of that, let me first take a moment to talk about why we use gradients in the first place. So, the human brain is a hugely complex structure. And if we want to do whole brain network analyses, we have to simplify it in order to make sense of it. One way in which we can do this is by parcellating the human brain. Now, this already dates back to at least the early 20th century with the release of the Brodmann Atlas. Brodmann defined regions of the brain based on cytoarchitecture. And we have continued with this throughout the history of neuroscience, with many neuroanatomists creating their own atlases, and once MRI became big, many neuroimagers creating their own as well. For example, the Euclidean Atlas based on functional connectivity of the human brain. However, whenever we parcellate the human brain, we always make an implicit assumption, which is that we assume that there are hard boundaries in the brain, and we assume that the regions that we define are homogeneous. And this is close enough to the truth that we can generally work with it. Now, so for most of our analyses, this is fine. However, imagine that you have a hypothesis that specifically states that there are gradual changes in the cortex. And in that case, you can't really assume hard boundaries anymore. And just to illustrate that with a real hypothesis, consider the tethering hypothesis. In a nutshell, it states that the sensory regions of the human brain are very closely regulated by molecular cues during development. But the further you move away from these regions, the more the development is regulated by self-regulatory mechanisms. So this implies a gradual change along the cortex. It's a function of distance. And this is where gradient techniques can come in. So what is a gradient? Well, here on the right, you see the first and second gradients of functional connectivity of the human connectome. The first gradient describes the biggest change in functional connectivity in the connectome, here between the default mode and sensory cortices. The second gradient describes the second biggest axis of variance in the connectome, here between the sensory cortices. Now, the similarity in color denotes how similar connectivity is. So dark red colors have very similar connectivity to other regions in dark red. We don't have to define any a priori boundaries or regions. And it allows for these multiple overlapping gradients for multiple overlapping changes in functional connectivity. So what can we do with this type of analysis? Well, first of all, it simply allows for a decomposition of a whole brain connectome, as I just showed you in this image. We don't have to limit ourselves to the whole brain. We can also do this at a regional level, as was, for example, done with the cerebellar gradients of Kuhl et al. We can also compare across different groups or different cohorts. For example, in a study by Sukjun Hung et al., we calculated the gradients for healthy controls in the Abide dataset and for autism spectrum disorder in the Abide dataset. And what we found was that the default mode network in autism spectrum disorder is far less separated from the rest of the brain, as you can see from gradient 1. And this denotes a decrease in the decoupling between the default mode network and the rest of the brain in autism spectrum disorder. Now, these are all things that we can do with just the gradients alone. However, we can, of course, also compare these gradients to other markers. For example, Julia Huntenberg et al., they found that the first axis of functional connectivity, the first gradient, which describes the largest variance in functional connectivity, is related to intracortical myelination. Another example was from Charlotte Murphy et al., who stratified their findings based on a gradient. So they had a 0-back and 1-back task. And as you can see, the parameter estimates for the 0-back task are far higher in the unimodal area, and the parameter estimates for the 1-back task are higher in the higher order areas. Now, all of that is still always working with one gradient at a time. We can also work with multiple gradients at the same time, and here we start referring to what we call gradient space. So gradient space is essentially just the space encompassed by the first few gradient vectors. So here's a two-dimensional gradient space. You can see gradients 1 and gradient 2 on the y and x axis, with each point simply colored by their position in gradient space. And this provides us with a lower dimensional space for connectivity visualization and analysis. And just to show you one example of how we can use this, consider again the study I was just referring to on the differences between healthy controls and autism spectrum disorders in terms of their functional gradients. Here again, on the y-axis, we have gradient 1, on the x-axis, we have gradient 2, and at the top, we simply see these color-coded by their community membership to the DEO networks. In red, the default mode, in purple, the visual, in blue, the somatomotor, and in gray, everything else. Now, At the top, we can then again see the same difference I was just referring to. That the first gradient is contracted in autism spectrum disorder. You can see that in the shift in the default mode network nodes. Now, if we look at the bottom half of this image, we see an analysis of stepwise functional connectivity. Essentially what this is if you place a seed in, for example, the somatomotor cortex, and then you move from there to its connected nodes, and from there you move to its connected nodes again. You keep repeating this process without going back to nodes where you've already been. Then you would start to travel through the connector. Now, if you do this in healthy controls and you start in any of the sensory regions, then you'll slowly move up towards the default mode, as you can see in the image in the bottom left. The visual seed in the bottom left, the somatomotor and auditory seeds in the bottom right. The stepwise connectivity moves up to the default mode network. So the signals moving from the unimodal to transmodal areas. If we do the same thing in autism spectrum disorder, we find a very different result, in that the stepwise connectivity from the visual cortex in the bottom left just kind of stays stuck there. And the stepwise connectivities from auditory and sensory cortices initially moving toward default mode, but then veering off into another direction. So these are just some examples to illustrate the kinds of analyses that we can do with gradients. We can decompose the functional connectome and just use that decomposition itself. We can relate it to particular markers of cortical organization, and we can use it to assess other methodologies such as stepwise connectivity. So how do we actually build these gradients? How do we make them ourselves? And how could you do this with your own data set? Well, we start off with some input data. In all the examples I've shown you, this is a functional connectivity matrix, but it can be any matrix. We then compute what we call an affinity matrix. The affinity matrix is essentially a neo matrix that denotes the similarity between each of the seed regions. High values denote high similarity, low values denote low similarity. So at its simplest, you could simply take a Pearson correlation of each pair of rows, and this could be an affinity matrix. In this example, we're using the cosine similarity, which is a metric quite closely related to the Pearson correlation. Next, we apply a dimensionality reduction step. At its simplest, this could be a principal component analysis. We tend to use diffusion map embedding, which is essentially a nonlinear principal component analysis. Whichever dimensionality reduction method you use, you'll end up with a set of eigenvectors, which we call gradients. And again, we could plot those and get a very similar image to the one I've shown you before. If all of that sounded very complicated, we tried to make it very easy. We've recently published a toolbox called Brainspace. This is a toolbox that's available in both Python and in MATLAB for the computation, statistical analysis, and the visualization of gradients. Documentation for this is also available on ReadDocs. All the code is open source and available on GitHub. There will be a link to this at the end of the presentation. Before I continue, just tell you a little bit about Brainspace and what you can do with it, how it works. Let me just give a quick shout out to a few other gradient toolboxes and toolkits that are out there. There is MapAlign by Satra Ghosh, which is a diffusion map embedding package that was used by Daniel Margulies during his 2016 study. There's conic topping mapping from Koen Haak's group, which is a slightly different way of computing gradients. It's intended more to be used at a regional level than at a whole brain level. And there's the package for the cerebellum gradients that I showed you before. So what can we do with Brainspace? Well, let's start off with the code for building a simple grade. And I'm in this presentation only showing you the MATLAB code. The Python code is very similar. If you go to our online tutorials, you see very similar Python code to this there. But in MATLAB code. So on the first line, we instantiate a gradient maps object. This is sort of the core object that does all the computations for you. Next, we fit a connectivity matrix with this object, and we can extract the gradients from that. The gradients are now computed. So we extract the first two gradients, and then we plot those on the cortex using the plot hemispheres function that is included in BrainSpace. And you can see that the first gradient that's computed is the default mode to sensory that you're now familiar with, and the second gradient is the sensory. And the second gradient is the sensory gradient that you've seen before. Now this is how you can construct a simple gradient that you can use in your analyses. However, consider for a moment that you might also want to compare different cohorts, different subjects, different populations of any kind. You'd have to compute gradients for each group or each subject separately. The problem with that is that you might run that when you run a dimensionality reduction step, the eigenvectors that are found might not be in the same space as each other. Fortunately, this is something we can very easily resolve by running an alignment after computing our gradients. This alignment most commonly is a Procrustes analysis. And this is very simple in BrainSpace. We simply instantiate a gradient maps object using the alignment parameter with the PA value, PA standing for Procrustes alignment. And then we fit it to our connectivity matrices, here providing multiple because we have two groups. And then we can plot our unaligned gradients here at the top and the aligned gradients here at the bottom. And as you can see, in the unaligned version, the first gradient flips around. This is something that very commonly happens in group 2. And after the alignment, both of the gradients are in the same space, and we can use these in our subsequent analyses. Now, the last point I want to talk about is null models. So, in any neuroimaging analysis that we do, but especially so with gradients, we should be wary of spatial autocorrelation in the data. What that means is if I know the value of any one voxel, then I have a pretty good idea of what the values of the voxels around it are. This is the spatial autocorrelation. The problem with that is that most statistical models assume independence of measurements. But the spatial autocorrelation means that our data points are no longer independent, and therefore our test statistics are biased. Now, BrainSpace implements two ways of resolving it, spin test and more spectral randomization. I'll just show you spin test here. The essential idea here is that we generate 1,000 distributions with the same amount of spatial autocorrelation, but different data. And so instead of just running a statistical test and computing a p-value, we instead compute a test statistic for the true data, 1,000 test statistics for the quote-unquote random data, and then we see in what percentile of the distribution our true test statistic lies. Now in BrainSpace, we simply run the spin permutations code. We supply it with the values that we want to permute, here the T1 of T2 intensity. We provide it with spheres corresponding to the surfaces. This is provided by default by both FreeSurfer and Civet, and the number of permutations. And how this works, you can basically see at the bottom. We have our T1 over T2 intensity, and we want to compare this to gradient 1. We project the T1 over T2 intensity to the sphere. We then rotate that sphere and project the data back to the surface. You can see that the data which used to be at the somatomotor cortex then ends up, in this particular example, in the visual and parietal cortices. We do this 1,000 times, giving us 1,000 distributions. And for each of these, we run a Spearman correlation with the original gradient, and we get the distribution that we see here on the right. And then we can see the true correlation in the dashed line on the left-hand side, which falls below the 2.5th percentile, so we judge it to be significant. So this is all I wanted to show you for just the basics of what BrainSpace can do and how to run it. So just to wrap up, gradients allow us to have a low-dimensional summary of high-dimensional data. We can use this to relate connectivity to other markers, such as intercortical myelin content, cortical thickness, stepwise functional connectivity, you name it. And these are very easy and fun to build with BrainSpace. Now, with that, there are many people that I'd like to thank for helping me get BrainSpace off the ground. In particular, to give a few shout outs to Boris and Wally, who both worked tirelessly with me to get this package up and running. And if you're currently on the European part of this Brainhack, special thanks to Casey, who is currently here to answer any questions you might have, because I am not a morning person. If you have any questions, Casey will be here to answer them. If you come up with any questions after the talk, you can tweet at me at reinervostiwal. You can email me at reiner.vostiwal.com. The link to our documentation is also there at brainspace.readthedocs.org. The documentation also has links to our GitHub and to the manuscript, so you can find both of those there. And with that, I'd like to thank all of you for listening, and I'll take any questions, or Casey will take any questions.